What hidden force links an apple's fall to the moon's orbit? How does gravity's whisper reach across the vast emptiness of space? Could this same quiet pull shape even the darkest abysses of the cosmos? On a clear night ages ago, a lone figure lies beneath a canopy of stars. The air is still and cool. Above, countless points of light shimmer against a vast darkness. Each star glints softly, like distant campfires in some other realm. In that quiet moment, there is wonder and a gentle hum of mystery. The person gazes upward, heart filled with curiosity and awe at the sight of the night sky. For early humans, the stars were more than just lights. They were lanterns hung in the heavens, perhaps guiding spirits or gods, or maybe ancestors watching from the darkness above. Some imagined the sky as a great dome or tent over the world, with tiny holes through which celestial light leaked down. Others saw the Milky Way as the glowing path of departed souls, or a river of milk spilled by divine hands. In every culture, stories bloomed among the stars, each tale an attempt to explain those silent lights and the deep darkness that holds them. Between the stars lay the unknown. The dark stretches between the constellations seemed like bottomless wells, profound and unfathomable. What lay in that endless black? Was it an infinite expanse going on forever, or a velvet curtain hiding another world beyond? To eyes without telescopes, the night was both beautiful and a little terrifying. Beautiful in its glittering lights, terrifying in its limitless shadow. One might feel the sky could swallow them up if they stared too long. It was a mystery without edges, a puzzle without an answer. Under such skies, our ancestors felt small. They sensed that beyond the glow of the campfire and past the edge of their familiar world stretched a vastness they could barely imagine. Sometimes they gave names to the darkness, chaos, the abyss, the great beyond, names that hinted at an endless depth. Perhaps, in their own way, they wondered about cosmic abysses, places where even light does not reach. The night invited questions that echoed quietly in the human mind. How high do the heavens go? What lies in the farthest darkness between the stars? Could there be chasms out there, great gulfs in the cosmos unknown to us? Such questions might have gently tugged at their thoughts as they drifted to sleep under that tapestry of stars. For thousands of years, the stars remained points of mystery. People charted their movements, noting how they wheeled around the sky each night, and how certain patterns returned every season. But the true nature of those lights stayed elusive. Were they distant fires, as some believed, the eyes of gods, or something else entirely? And what kept them there, placed in the sky as if by an unseen hand? As the ages passed, curiosity only grew. Wise observers in ancient Greece, India, China, and elsewhere tried to make sense of the cosmos, and slowly, ideas began to take shape. Some philosophers even dared to whisper that the universe might be infinite, extending without end into the darkness. The notion of an infinite space, a limitless void stretching beyond the stars, was a radical, haunting thought. An infinite cosmos could contain wonders and horrors beyond imagining. It was both wondrous and unsettling, like standing at the edge of a great precipice and peering into a bottomless chasm. In time, patterns were recognized in the stellar scatter. Groups of stars that formed pictures of animals, heroes, and gods. Ancient astronomers connected the dots to create constellations, a hunter chasing his prey, a great bear forever turning around the North Star, a swan gliding along the Milky Way. These familiar shapes brought comfort, a sense of order against the backdrop of the unknown. Yet even as people found pictures in the stars, the fundamental enigma remained. The stars were constant companions in the sky, but also unreachable, separated by distances one could hardly fathom. They twinkled each night, but no ladder could ever reach them. No bird could ever fly so high. A few early thinkers voiced extraordinary ideas. Perhaps, mused some in ancient Greece, those stars were not holes or fires on a solid dome at all. Maybe they were other suns like our own, shining from incredible distances. If that were true, then the universe was far larger than anyone had imagined. An infinite cosmos, endless space filled with countless stars, was a breathtaking and frightening concept. Most people could not grasp such immensity. It was easier to imagine a cozy sky with a fixed number of lights hung by divine hands. But the seed of a grander idea was planted, and it lingered quietly in human thought, waiting for evidence and reason to catch up. Despite all the stories and early theories, much of the cosmos remained hidden. The night beckoned with questions. What keeps the stars moving in their paths? Why don't they fall down? Is there something out there holding them in place, some force or mechanism? In the slow march of time, human curiosity pushed onward. The answers would not come quickly or easily, but they were coming. Far in the future of those first stargazers, centuries down the line, a great mind would finally decipher part of this mystery. That scientist would explain how an invisible pull, gentle yet persistent, holds moons, planets, and stars in their courses. In the silence of those ancient nights, a foundation was laid, a deep curiosity and reverence for the night sky. That quiet wonder, passed down through stories and careful observation, was the first step on a long path, a path leading toward the understanding of black holes, those ultimate cosmic abysses. But before reaching that distant destination, humankind first had to learn about the force that orchestrates the dance of stars and planets, a force unseen but ever present. It was time for gravity to enter the story. In the 17th century, as science blossomed in Europe, a breakthrough came in understanding this mysterious force. At its heart was a young mathematician and physicist named Isaac Newton. Legend tells of Newton observing an apple fall from a tree one quiet day in the late 1600s. Perhaps he was resting in an orchard, lost in thought, when he saw the apple drop to the ground with a soft thump. It was an ordinary event, something that happens countless times. But to Newton, it sparked an extraordinary question. What made the apple fall down instead of drifting upward or sideways? Why did it fall at all? Newton considered that the apple was pulled to earth by an invisible force. He called that force gravity. Then came a leap of imagination. If gravity reaches the treetop to tug on an apple, could that same force reach even higher? Could it extend to the clouds, to the very moon? After all, the moon circles the earth. Perhaps it is falling too, falling around the earth rather than straight down. Newton imagined that the moon is like a projectile launched so fast that as it falls, the Earth's curved surface continually drops away beneath it. Thus, the moon never hits the ground, it keeps circling in an endless fall. This was a radical idea for its time, that the motions of the heavens and the motions on Earth might be governed by the same force. In his mind's eye, Newton pictured a very tall mountain, so high that it rose above the air of Earth's atmosphere. On its peak, a cannon fires a cannonball. Fire it gently, and the cannonball arcs a short distance before falling back to the ground. Fire it faster, and the cannonball flies farther before curving downward. Increase the speed further, and the arc of its path grows larger and larger. Newton realized that if the cannonball could be fired fast enough, it would fall completely around the Earth, never landing at all. It would be in orbit. And if it went faster still, eventually the cannonball would break free of Earth's gravity entirely and not return. This critical speed is what we now call escape velocity. For Earth, that escape speed is about 11 kilometers per second, far beyond the reach of any cannon in Newton's day, faster than any bullet ever fired. Newton's thought experiment demonstrated that gravity isn't a force that stops at the treetops or even the clouds. It extends far out into space, growing weaker with distance, but never truly disappearing. Building on this insight, Newton formulated the law of universal gravitation. Every object in the universe, he found, pulls on every other object with this invisible force. The more massive an object is, or the closer two objects are, the stronger the gravitational pull between them. If you double the distance between two bodies, the gravitational force becomes 4 times weaker. This simple yet profound rule explained both why planets stay in orbit and why apples fall downward. Suddenly, the cosmic dance revealed a comprehensible pattern. The same gravity that causes an apple to drop also guides the moon in its graceful loop around Earth and keeps the planets bound in their paths around the distant sun. For the first time, the heavens and the Earth were unified under one natural law. No longer did one need crystal spheres or divine intervention to explain the planet's motions. Gravity alone, quiet and steadfast, was enough. Newton himself marveled at how this unseen force could act across the emptiness of space. He spoke of how each mass whispers an attraction across the void to every other mass, a pull that can traverse even the great distances between the stars. Though he couldn't explain how gravity worked at a distance, the mechanism of this eerie action across space, he knew its effects could be described with precision. With Newton's equations, one could predict the orbit of a comet or the fall of a stone with equal confidence. Newton's discovery was like turning on a gentle light in a dark room. A mysterious, invisible influence was given a name and a mathematical form. The universe was not held together by magic or by crystal spheres, but by a natural force that humans could finally begin to understand. Anyone gazing at the night sky now knew that, as distant as those stars were, a subtle bond connected us to them. A delicate gravitational thread linked the Earth to the moon to the sun to the stars, and all stars to each other in a vast cosmic web. It was a comforting and humbling realization. The entire cosmos tied together by this quiet force, this gravity that whispers across the darkness. Now that humanity had identified this universal pull, new questions emerged. How strong could gravity become? If the fall of a simple apple revealed this force, what might a massive star's gravity do? Newton's laws gave scientists the tools to calculate the gravitational pull of planets and even of stars. And with those tools in hand, some daring minds began to wonder about extreme possibilities. Could there be places in the universe where gravity's whisper becomes a shout, where its pull grows so overwhelming that it dominates everything nearby? The stage was set for one of the most astonishing ideas yet. The possibility of a star so heavy and so dense that not even light could break free from its gravitational grip. Decades and centuries rolled by, and this question of gravity's ultimate power quietly took root in scientific minds. Armed with Newton's laws, Thinkers in the 1700s began to wonder, could a star's own gravity eventually overwhelm its light? Stars were understood to be enormous blazing spheres. If gravity always pulls inward, might a star one day collapse under its own weight? It was a bold line of speculation, far ahead of any observational proof. In the late 18th century, an English natural philosopher and clergyman named John Michell decided to explore this extreme idea. Michell was a curious and insightful thinker, living in a quiet village and gazing up at the same night sky that had inspired wonder for millennia. In 1783, he penned a letter outlining a startling hypothesis. Using Newton's equations, Michell imagined a star much larger and heavier than our Sun. He calculated how strong gravity would be at the surface of such a hypothetical star. The numbers led him to an astonishing conclusion. If a star was sufficiently massive and compact, its gravity could become so intense that the star's light would not be able to escape. In effect, the star could be invisible, a brilliant fire hidden in plain sight by its own tremendous gravity. Michell reasoned that for a massive enough star, the inward pull would be irresistible. Any ray of light trying to leave such a star would be dragged back by gravity's grip. The star might shine fiercely inside, but none of that light would ever reach distant eyes. It would be as if the star had collapsed into darkness under the weight of its own attraction. Michell imagined a very large star, perhaps hundreds of times the Sun's size, exhibiting this property. Though he didn't use the term, later generations would call such an object a dark star. It was, in a sense, the first rough sketch of what we now call a black hole, a place where gravity is so strong that not even light can break free. A few years after Michell's proposal, across the English Channel, the renowned French mathematician Pierre-Simon Laplace arrived at a similar idea. In 1796, Laplace wrote about the possibility of what he called an invisible star. If a star were sufficiently massive, he noted, it would exert such a powerful gravitational pull that light itself could not get away. Laplace initially included this conjecture in the first edition of one of his books, intrigued by the notion. However, in later editions, he removed the reference, perhaps finding the concept too speculative, or perhaps because the science of light was evolving. By the early 19th century, many physicists had come to understand light as a wave rather than a stream of particles. And if light was a weightless wave, how could gravity, which pulls on mass, ever trap it? Without solid evidence, the dark star idea drifted into the background. To most scientists of the 1800s, Michell's dark star was more a mathematical curiosity than a credible reality. It was an intriguing thought experiment, but unproven and seemingly untestable at the time. Yet it planted a seed that would bide its time. On paper, Michell had shown that gravity might have no theoretical limit, that given enough mass in a small enough space, a star's gravity could effectively cause it to stop shining. Gravity's whisper could crescendo to a roar and then to a deafening silence, the star's light silenced by its own pull. Though largely forgotten throughout the 19th century, Michell's insight was truly ahead of its time. He even speculated on a way one might find such invisible stars. He suggested that some visible stars might be orbiting unseen companions. If a visible star wobbled or circled around an empty patch of sky, that emptiness might harbour a massive dark star tugging on it. This remarkably prescient idea foreshadowed the methods astronomers would use much later to detect black holes, observing the motion of stars and gas around an invisible centre. In Michell's era, however, these ideas were simply too far ahead. Technology wasn't advanced enough to confirm them. and the theoretical framework to fully understand them was not yet in place. The notion of a collapsing sun, a star that caves in or traps its own light, remained suspended in the realm of conjecture. Still, the idea never vanished entirely. It lingered like a half-remembered dream in the halls of science, waiting for the right moment and the right theory to re-emerge with full force. The next piece of the puzzle was to understand more rigorously what it means to escape gravity, and conversely, what it means to be trapped by it. Michel had introduced the concept, but to truly grasp a dark star, one had to examine the idea of escape velocity in detail, especially when even light is at stake. So, what exactly is escape velocity? And at what point does even light meet its match and turn back? Answering those questions would illuminate how a star could be caught in its own gravitational grip. To better grasp Michel's dark star idea, it helps to think more about escape velocity, the speed needed to break free from a body's gravitational pull. We touched on this concept with Newton's cannonball thought experiment. On Earth, if you toss a ball upward, it will slow down and fall back because it isn't fast enough to escape Earth's gravity. A rocket, on the other hand, must reach about 11 kilometers per second, around 40,000 kilometers per hour, to completely escape Earth's gravitational pull and soar off into space. That speed, about 11 kilometers per second, is Earth's escape velocity. Every celestial body has its own escape velocity, depending on its mass and size. The more massive an object, and the more compact its mass, the higher the escape velocity from its surface. Now, consider something far heavier than Earth, like the Sun. The Sun is much more massive, so the escape velocity from the Sun's surface is far higher, roughly 55 times greater than Earth's. In fact, to leave the Sun's gravity starting from its surface, you'd need to travel around 600 kilometers per second. That's about 0.2% of the speed of light. Still within the realm of physical possibility, perhaps, but far beyond anything humans have ever achieved with spacecraft. Michel pushed this idea to the extreme. He asked, what if there were an object with an escape velocity equal to or exceeding the speed of light itself? The speed of light is about 300,000 kilometers per second, a cosmic speed limit that nothing can surpass. If a star's gravity were so strong that you'd need to go faster than light to escape it, then it follows that light itself could not escape at all. In that case, the star's light would be trapped. Imagine a beam of light leaving the surface of such a massive star. It races upward, but gravity tugs at it relentlessly. In Newton's picture, you could imagine that beam of light slowing down as it climbs away, losing more and more speed, until at last it stops and is pulled right back down. It's a strange image, light rising, pausing, and then falling like a tossed ball. Yet that's essentially what Michel proposed. Any light that star tried to emit would go outwards, hesitate, and then come right back, drawn home by gravity. This phenomenon of light being unable to escape gives escape and return its name. Anything thrown upward from that star without sufficient speed would return, be it a stone, a rocket, or a ray of light. To a distant observer, such a star would effectively disappear from view. No glimmer of it could reach their eyes. It wouldn't matter how brightly it burned, or how fiercely it shined inside. None of that light would overcome the enormous pull at the star's surface. The star would be like a glowing furnace locked behind a one-way door. Light could check out from the surface, but it couldn't get away. Gravity would always drag it back. Michel even put numbers to this idea. He imagined a star of the same density as our Sun, but vastly larger, hundreds of times bigger in diameter. Such a star, according to his calculation, would have an escape velocity at its surface equal to the speed of light. In that scenario, any particle of light trying to escape would just fail to do so. If the star were made even denser or more massive, the escape velocity would exceed light's speed, and the trap would be even more absolute. In 18th century terms, this was an invisible star or dark star. In modern terms, Michel had essentially identified the critical condition for a black hole. When the escape velocity from an object's surface reaches the speed of light, an event horizon forms, a boundary beyond which nothing can return. It's important to note that Michel was working with the physics of his time. He and his contemporaries thought of light as possibly consisting of tiny particles, Newton's corpuscles, that gravity could pull on. Under that assumption, his reasoning was sound. If light were made of little flying particles, and if gravity tugged on those particles just as it does on apples and cannonballs, then a sufficiently massive star would indeed hold its light captive. Today we understand that light behaves both like a wave and a particle, and it has no rest mass. But remarkably, Michel's conclusion remains valid in a deeper sense. Only the explanation has changed. Gravity can affect light not by pulling on a mass, but by warping the space the light moves through. Michel anticipated the result, even if he didn't have the later insight of how it really works. So imagine standing at a safe distance and watching such a massive dark star. What would you see? The answer is almost nothing at all. The star would not be visible to your eyes. You might not even suspect anything was there, unless you noticed the telltale dance of other objects around an apparently empty region of space. Perhaps you'd see a nearby star circling a point in the darkness, tugged by a partner it itself does not illuminate. The presence of the dark star could only be inferred by its gravitational effects on its surroundings, not by any light of its own. This eerie concept, a star that can be felt but never seen, must have sounded like a ghost story in the halls of 18th century science. In the late 1700s and through the 1800s, this notion didn't advance much further. There was no way then to test it, and with new theories of light emerging, the idea lay dormant. Yet it was not forgotten. It stayed quietly in the background, waiting. The next great leap would not come from finding an actual dark star with a telescope, but from a radical change in our understanding of gravity itself. Michel's dark star was like a bridge to something even more profound, a hint that Newton's picture of gravity, as powerful as it was, might not be the final story when it came to such cosmic extremes. To bring the dark star concept fully into the fold of science, a new theory was needed, one that could marry gravity with the true nature of light. Throughout the 1800s, physics progressed in leaps and bounds, slowly setting the stage for a new understanding of gravity. By the late 19th century, James Clerk Maxwell had formulated his landmark equations of electromagnetism, revealing that light is an electromagnetic wave that travels at a constant speed. This was revolutionary. It hinted that the speed of light might be a fundamental limit built into the laws of nature. Then came the famous Michelson-Morley experiment of 1887. Scientists Albert Michelson and Edward Morley tried to detect the Earth's motion through a supposed luminiferous ether, an invisible medium then thought to carry light waves. To their surprise, the experiment found nothing, no change in the speed of light due to Earth's motion. No matter how they oriented their apparatus or how the Earth moved, light's speed appeared the same. This puzzling result defied the common sense of Newtonian physics and cried out for an explanation. Meanwhile, astronomers had their own nagging mystery. The planet Mercury, smallest and closest to the Sun, was not following its orbit exactly as Newton's theory predicted. With each circuit around the Sun, Mercury's closest point of approach, its perihelion, shifted forward slightly more than it should have. The discrepancy was tiny, an extra turn of about 43 arcseconds per century, but real and measurable. For decades, astronomers scratched their heads. Some hypothesized an unseen planet inside Mercury's orbit, cheekily dubbed Vulcan, whose gravitational pull could account for the anomaly. But despite eager searches, no such planet was ever found. It seemed as if Newton's theory, so successful elsewhere, might be showing a small crack when examined under the most precise observations. By the start of the 20th century, physics was brimming with questions like these. How could light always move at the same speed, regardless of how one moved relative to it? What was the true nature of time and space themselves? And what was causing Mercury's orbit to misbehave? These puzzles were like distant thunder, heralding an oncoming storm in science. The old framework was straining at the seams. Something new was needed to make sense of it all. In 1905, a quiet patent clerk in Switzerland offered one piece of the answer. His name was Albert Einstein. In that miraculous year, Einstein published his special theory of relativity, which radically redefined the concepts of space and time. One of its core principles was that the speed of light in a vacuum is constant, a universal speed limit that all observers, no matter how they move, will measure as the same. To accommodate this strange but true fact, Einstein showed that measurements of time and space must adjust. Time can flow at different rates for different observers, time can dilate, and lengths can contract when objects move very fast. These effects are negligible in everyday life, but become crucial at speeds approaching that of light. Special relativity was a profound breakthrough that answered the riddle of the Michelson-Morley experiment and honored Maxwell's unchanging light speed. Space and time were no longer absolute. They were interwoven and relative, part of a four-dimensional fabric of reality. Special relativity, however, left gravity untouched. It was like solving one part of a puzzle while another central piece remained missing. Einstein soon turned his thoughts to that missing piece, gravity itself. He suspected that gravity, too, would need to be reconceived to fit into this new relativistic picture of the universe. Over the next decade, Einstein worked tirelessly on the problem of gravity. He was guided by a simple but profound insight known as the equivalence principle. It came from an elegant thought experiment. Imagine you are in a closed room with no windows. If you feel a force pressing you to the floor, is it because you're on Earth experiencing gravity? Or because the room is actually aboard a rocket ship that's accelerating through space? Einstein realized that there is no observable difference. Being in freefall, where gravity is the only force acting on you, feels the same as floating weightless, and feeling weight on your feet could mean you're under gravity or simply accelerating upward. This equivalence between acceleration and gravity suggested a new way to think about gravitational force. Einstein eventually had a revelatory idea. What we experience as gravity is actually the effect of curved space-time. Mass, like that of the Earth or the Sun, warps the geometry of space and time around it. Objects, and even beams of light, simply follow the curves and contours of this warped space-time. In November 1915, Einstein unveiled his general theory of relativity to the world. It was an elegant, if mathematically complex, description of gravity. No longer a mysterious force reaching across space, but rather the shape of space and time themselves, molded by mass and energy. In Einstein's new picture, a planet orbits a star, not because it's pulled by an unseen hand, but because it's rolling along a curve in the warped fabric of space-time that the star creates. Likewise, a ray of starlight passing near the sun bends around it, not because the light has weight and is pulled, but because the sun's mass makes space curve, and the light follows that curved path. general relativity was quickly put to the test. One of Einstein's first triumphs came almost immediately. His equations naturally explained the odd behavior of Mercury's orbit. The extra 43 arcseconds per century of Mercury's perihelion advance fell right out of the theory, with beautiful precision and no need for hypothetical planets or ad hoc fixes. A few years later, in 1919, came a dramatic confirmation. During a total solar eclipse, astronomers were able to observe stars in the sky close to the darkened sun. The sun's gravity, Einstein had predicted, would bend their light, making the stars appear slightly out of place. And indeed, when the eclipse came and careful measurements were made, the stars' positions shifted exactly as Einstein's theory said they would. Light, it turned out, did bend in a gravitational field, just as Michel long ago had imagined, though for very different reasons. Einstein became an overnight celebrity, and general relativity was hailed as a new cornerstone of physics. With Einstein's theory in hand, the concept of an object trapping light suddenly had a solid foundation. Gravity in this new view didn't need to grab light with an invisible force. Instead, a massive object could warp space so severely that all possible paths light could take curved back inward. In the language of general relativity, if enough mass is concentrated in a small enough volume, the curvature of spacetime around it becomes so steep that it's like a pit with no way out. All routes outward lead back down. This is essentially a modern description of what Michel had imagined with his dark star, now understood not as a Newtonian oddity, but as a natural consequence of curved space and time. At first, even Einstein was not entirely sure what his equations implied about extremely dense masses. The idea of black holes was not immediately obvious to everyone, but the mathematics was sitting there, ready for someone to explore it. Just a few months after Einstein published his theory, a German physicist named Karl Schwarzschild found a solution to Einstein's gravitational equations that described the space-time around a spherical mass. Buried in this solution was something extraordinary. A critical radius, now called the Schwarzschild radius, for any given mass, within which space-time curvature becomes so extreme that nothing, not even light, can escape. In other words, Schwarzschild's solution was the theoretical confirmation of a dark star in Einstein's universe. It was as if Michel's idea had been woven into the fabric of space-time itself. General relativity predicted that black holes could indeed exist. Neither Einstein nor Schwarzschild called these objects black holes at the time. They often referred to them in more abstract terms, like frozen stars, or simply considered them an odd feature of the math. In fact, for many years, even Einstein himself was skeptical that nature would actually form such extreme objects. Some of his contemporaries thought the idea was too strange to be real, that perhaps some unknown mechanism would prevent stars from collapsing to that degree. The term black hole would not be coined until the 1960s, when the reality of these objects began to gain acceptance. But the essential idea was now on firm scientific ground. What had begun as a wild 18th century thought experiment was emerging as a genuine prediction of our best physical theory. Thus, the era of mere speculation was over. The concept of being caught in a black hole's grip was no longer science fiction or philosophical fancy, but a real possibility allowed by known physics. Of course, the story was far from finished. Indeed, it was only beginning. Scientists would soon grapple with how such objects form, what happens inside them, and how we might detect them from light years away. But one thing had become clear. Those cosmic abysses that early sky gazers had only dreamed about were grounded in reality at last. The long journey, beginning with ancient wonder at the night sky, leading through Newton's discovery of gravity, and onto Michel's dark star and Einstein's curved spacetime, had brought us to the threshold of understanding black holes. And so, we end this part of the journey at a profound threshold. The next steps will delve deeper into the nature of these mysterious black holes, how they grow and pull in matter, how they influence the galaxies around them, and what ultimate mysteries lie at their core. Our story will continue, drawing us ever closer to that ultimate abyss, the event horizon, and even beyond, into the dark heart of a black hole. In the early 20th century, our understanding of gravity was on the brink of a profound transformation. For more than 2 centuries, Isaac Newton's picture of gravity had reigned supreme, an invisible force reaching across space, pulling planets in their orbits and apples to the ground. This view of gravity was powerful and predictive, yet it left questions lingering in the silence of space. How did this force act across the void without any physical connection? And could there be more to the story of gravity than a simple pull between masses? A bold new idea began to take shape in the mind of Albert Einstein. He imagined that space and time were not the static, separate backdrop Newton had assumed, but instead were part of a unified, flexible fabric, space-time, that could bend, stretch, and even ripple. Einstein had already demonstrated a decade earlier, through his special relativity theory, that space and time are intertwined dimensions. Now, in 1915, he extended this revolutionary thinking to gravity, proposing that it too must be understood in terms of space-time. He unveiled his general theory of relativity, which redefined gravity not as an invisible pull, but as a curving of space-time caused by mass and energy. In Einstein's new description, gravity is the very shape of space-time itself, bending around a mass. Massive objects like the Sun or Earth distort the geometry of the space and time around them. Other objects simply follow the curves and slopes of that distorted space-time, much as a marble rolls along the dimple in a warped surface. One of Einstein's key insights on this journey came from a simple thought experiment about falling. He imagined a person inside a closed elevator cabin. If the elevator were falling freely under gravity, the person would float off the floor, weightless, as if gravity had been switched off. Inside the cabin, there would be no way to tell the difference between free fall and floating in the zero gravity of deep space. This realization, which Einstein later called the happiest thought of my life, hinted that gravity and acceleration were 2 sides of the same coin. It suggested that being pulled by gravity is equivalent to accelerating in curved space and time. This was a profound clue that gravity might not be a force in the traditional sense, but rather a feature of space-time itself. To understand Einstein's idea, imagine space-time as a vast, stretchable fabric that responds to the presence of matter and energy. A massive object, like a star, is akin to a heavy ball placed on a taut rubber sheet. It creates a dip or dimple in the sheet. Planets orbiting the star are like marbles rolling around the slope of that dimple. They are not being pulled by an invisible string. Instead, they are following the curved paths in the warped space created by the star's mass. In this way, matter tells space-time how to curve, and the curvature of space-time tells matter how to move. The Sun's gravity, for example, is the result of the Sun bending the cosmic fabric around it, and Earth's motion is simply our planet coasting along the curve of that indentation. In Einstein's elegant picture, Space is not the only thing that bends. Time itself also warps in the presence of mass. A clock, deep in a gravitational field, say at sea level on Earth, ticks ever so slightly slower than a clock on a mountaintop or far out in space. Lengths can stretch or compress under strong gravity as well. Near a heavy object, the flow of time slows and distances distort. These effects are tiny in everyday life, but they become dramatic in extreme conditions. Einstein's theory revealed that an apple falls not because it is pulled by an unseen hand, but because it is following the curved space-time created by Earth. Gravity is the gentle guide of space-time that shapes the motion of objects. For the first time, gravity had a tangible medium, space itself. Such a revolutionary idea begged for proof, and nature provided a dramatic confirmation a few years later. In 1919, astronomers led by Arthur Eddington ventured to observe a total solar eclipse, aiming to test Einstein's prediction that light would bend around a massive body. During the eclipse, when the sun's glare was blotted out, they took photographs of stars near the sun's edge. The starlight passing close to the sun was indeed deflected. The stars appeared slightly out of position, exactly as Einstein's equations had foretold. Space really does bend where gravity is strong. The expedition's measurements showed this clearly. The news made headlines worldwide, and Einstein, until then a relatively obscure scientist, became an overnight celebrity. The once abstract void between celestial bodies was now understood as something dynamic and alive with shape. The very fabric of reality could warp and curve, carrying planets, light, and everything else with it. This breakthrough set the stage for deeper mysteries. If space and time could be curved by matter, just how far could that curvature go? Most of the time, the warping of space-time is gentle, a slight dip here, a subtle bend there. But could space-time ever be warped to the breaking point, forming a bottomless well from which nothing could escape? Einstein's equations themselves hinted at such bizarre possibilities, though at first they seemed like mere curiosities of the math. Then, only a year after Einstein's eclipse triumph, a remarkable solution to his equations emerged that offered a tantalizing answer, and it came from an unexpected place. As scientists began to explore Einstein's formidable field equations, one of the first major discoveries emerged from the midst of World War I. In 1916, a German physicist named Karl Schwarzschild, stationed on the front lines at the time, managed to solve Einstein's equations for the simple case of a single spherical mass. It was an astonishing feat of concentration and insight, accomplished under the smoky skies of wartime. Schwarzschild's solution described in precise detail how space-time would curve around a solitary, non-rotating object like a perfectly spherical star. At ordinary distances from the mass, it mirrored Newton's familiar gravitational pull. But closer in, the mathematics revealed something extraordinary. Hidden in Schwarzschild's equations was a theoretical blueprint for a gravitational abyss, a region where space-time curvature would become so steep that not even light could climb out. In essence, the solution hinted at the existence of a point of no return around a collapsed mass. It was the first glimmer of what we now call a black hole, though at the time it was viewed purely as a mathematical oddity. Schwarzschild's solution introduced the concept of a critical radius, later known as the Schwarzschild radius, within which the gravity of a given mass would become overwhelming. If an object's entire mass could be compressed into a sphere smaller than this critical radius, space-time around it would curve so dramatically that all paths outward would bend back inward. In other words, anything, including light itself, that ventured closer than this radius would be trapped and unable to escape the object's gravity. This radius essentially marks the size of the object's event horizon. the boundary of no return for that mass. The Schwarzschild radius depends on the mass. For a mass as large as our Sun, this critical radius is only about 3 kilometers, incredibly small compared to the Sun's actual size of about 700,000 kilometers. For an object with Earth's mass, the Schwarzschild radius is around 9 millimeters, roughly the size of a marble. These figures illustrate just how extreme the conditions have to be to form such a gravity trap. An entire star would have to be crushed into a ball no larger than a town, or a planet into something you could hold in your hand. In 1916, it was hard for scientists to imagine any natural process that could achieve such fantastic compression, so the idea remained safely theoretical. Karl Schwarzschild himself likely did not grasp that he had found a description of what we now call a black hole. The term didn't exist yet, and the concept was too outlandish for most scientists to take seriously. His solution arrived just weeks after Einstein's theory was published, catching even Einstein by surprise with its elegance. Einstein praised Schwarzschild's mathematical ingenuity, but he and others regarded the Schwarzschild singularity, as the critical radius was nicknamed, as more of a mathematical oddity than a physical reality. It seemed absurd to think that a real star would ever shrink into such an extreme state. Many physicists assumed that the theory itself might break down under those conditions, or that some yet unknown force of nature would intervene long before a singularity could form. For years, the idea of a completely collapsed star remained an intellectual curiosity, a shadow lurking at the fringes of physics with very few believers. Even Einstein doubted that nature would allow such a bizarre object to actually form. Karl Schwarzschild, sadly, did not live to delve deeper into the implications of his solution. Serving in the army and weakened by illness, he passed away in the spring of 1916, only a few months after his groundbreaking paper was sent from the battlefield. The task of interpreting the true meaning of the cosmic singularity his equations had uncovered would fall to the next generation of physicists. His brief discovery, made under wartime skies, had opened the door to one of the universe's greatest mysteries, a door through which scientists would only cautiously step in the decades to come. At the heart of Schwarzschild's theoretical black hole lay something even more disconcerting than a one-way boundary. According to the mathematics, if a mass collapsed completely inside that critical radius, it would continue to contract all the way down to a single point at the center. All of the star's matter would be crushed into an infinitely small volume. The density at that point would become infinite, meaning all known concepts of space, time, and physical law would cease to make sense. This central point of endless gravity was given an ominous name: a singularity. A singularity is essentially a place where our current understanding of physics breaks down completely. In general relativity, it appears as a tear in the fabric of spacetime, a point of infinite curvature where the gravitational field has no limit. No one can truly describe what happens at such a point, because the equations yield infinities instead of meaningful answers. It is a realm where time and space themselves may lose their usual meaning. In a sense, the singularity marks the boundary of what we can predict. It is nature's way of telling us that our compass of physical law has hit a blank spot on the map. For Einstein, and many physicists of his generation, the idea of a true singularity in nature was deeply unsettling. It seemed to signal that the theory, or our understanding of it, was incomplete. Surely, they thought, real stars could not collapse into infinite density. Some new force or law of nature must intervene before that catastrophe. Einstein himself conjectured that rotation or other factors might prevent singularities from forming. Others suspected that perhaps quantum physics, not yet fully developed at the time, would eventually provide an answer to what happens at such extreme depths of gravity. For the moment, though, the singularity remained a ghost lurking in the equations, a spectre that hinted at both the power and the limits of Einstein's masterpiece. And yet, Einstein's theory offered a kind of cosmic censorship. If a singularity did form, it would be hidden behind a veil, an invisible boundary, later called the event horizon. In the final stage of a star's collapse, as densities become extreme, this one-way boundary would appear around the collapsing core, sealing the singularity off from the rest of the universe. Beyond that event horizon, nothing, not even light, could escape to reveal what was happening inside. Thus, any breakdown of physics at the core would remain hidden from outside observers. The event horizon is perhaps the most defining feature of a black hole. It isn't a physical surface like a planet's crust or a star's flame, but an invisible spherical boundary in space-time surrounding the collapsed mass. What makes this boundary special is a simple but absolute rule. Nothing that passes through it from the outside can ever return. It is a one-way door in the universe. Once you go in, you cannot come out. Imagine drifting through open space toward a massive, dark object. At first, you might not even realize you are near a black hole. There are no signposts or flashing warnings in the void. But as you slip closer, you would eventually cross an unseen threshold. If you drift inward past that point, the event horizon, there is no turning back. No amount of rocket thrust or desperate effort could reverse your course. Even the fastest thing in existence, light itself, cannot climb out once it has fallen past this boundary. That is why we call it a black hole. Beyond that shadowy line, not a single ray of light can escape to tell the outside world what has happened. The term event horizon is evocative. It signifies that beyond this horizon, no events can ever be seen or known by observers outside. It's as if any happenings inside simply disappear from the observable universe, cast into permanent shadow. From the outside looking in, strange things would occur at this boundary. If you watched a brave or foolhardy astronaut approach a black hole, you would see their motions slow down as they neared the horizon. It would be as though time itself were coming to a stop for them at that deadly border. Their spacecraft's clock would appear to tick more and more slowly. Any signals they sent, flashes of light or radio pulses, would get stretched to lower and lower frequencies, growing fainter and redder until the signals faded away. In fact, to your eyes, the astronaut would never be seen to fully cross the event horizon. They would dim and freeze in place at the boundary, their image eventually smearing into darkness under the extreme gravity. Of course, for the astronaut themselves, nothing so remarkable occurs at the horizon. They would fall straight through, without fanfare, unaware that an outside observer perceives their fall as an almost endless process. This strange discrepancy is a trick of perspective, caused by gravity's warping of time. To a distant observer, the event horizon is a kind of frozen halo where time stands still. But to the infalling traveller, it's just another point in space they pass on the way inward. For a long time, physicists struggled to fully understand the nature of the event horizon. Early on, some thought the horizon in Schwarzschild's solution was itself a kind of singularity, because the equations did seem to blow up at that radius. But later analysis showed that this was a mathematical illusion caused by the coordinate system used to describe spacetime, like having a map that makes the North Pole look like the end of the world. With a better choice of coordinates, one finds that nothing infinite happens at the event horizon. An object falling through experiences nothing special at that boundary. The The true singularity lies far deeper inside, at the core of the black hole. The event horizon is simply the outer boundary of the black hole's gravitational prison. Crossing the event horizon itself would not necessarily be lethal or even noticeable to an infalling traveler, particularly if the black hole is very large. Once inside, however, the pull of gravity continues to increase. In a stellar mass black hole, by the time you approach the central singularity, the tidal forces, the difference in gravity's pull between your head and your feet, become unimaginably huge. Long before you actually reach the singularity, those forces would rip you apart, stretching you into a thin strand of matter in a gruesome process nicknamed spaghettification. In a supermassive black hole, by contrast, the tidal forces near the horizon are much gentler. An astronaut falling into one might cross the event horizon without immediate harm or even much notice. But as they journey further inward, even in a giant black hole, the gravity will strengthen and eventually reach catastrophic levels. Either way, the event horizon is only the beginning of the end. It marks the point of no return. Beyond this boundary, the plunge toward the singularity is inevitable, and all hope of escape is gone. For a distant observer, the event horizon effectively acts like the surface of a black hole, a black sphere casting a round silhouette against any background light. Anything that crosses that surface vanishes from view, as if swallowed by a void. That is why black holes appear truly black. We cannot see past the horizon. We only infer the presence of the hidden mass by its gravitational effects on nearby stars, or by the hot gas glowing just outside the brink. The horizon's edge is the silhouette that astronomers now seek to capture as evidence of a black hole's presence, the dark shadow against the glowing backdrop of material swirling around it. In recent years, astronomers have even managed to capture images that reveal this phenomenon. By using a network of telescopes across Earth, they observed a glowing ring of gas and dust swirling around a dark center in the galaxy M87. That dark center is the shadow of a black hole's event horizon, essentially a silhouette of the point of no return. It is a profound sight, the first direct visual evidence of a black hole's presence, marking the boundary between our visible universe and a realm we cannot directly observe. Despite these theoretical developments, black holes were not immediately embraced by the scientific community. For decades after Schwarzschild's discovery, the idea of an object so extreme that it trapped light remained largely a speculative ghost story. Many scientists simply believed that such an outcome would never occur in reality. Even the terminology was lacking. The phrase black hole didn't exist yet. A few visionaries spoke of frozen stars or collapsed stars, but these notions stayed at the fringes. The reluctance was understandable. The concept was so extraordinary that it defied intuition. It would take further insights and mounting evidence to turn the black hole from an outlandish notion into an accepted reality. In the early 20th century, several leading scientists openly doubted that nature would ever form a black hole. Ironically, Albert Einstein, whose own equations predicted these objects, was among the skeptics. In 1939, Einstein wrote a paper arguing that no physical star could collapse all the way to a singularity. He believed that some pressure or rotation would always stop the contraction before the point of no return was reached. Likewise, the renowned astronomer Sir Arthur Eddington found the concept absurd. Eddington, who helped verify Einstein's theory by measuring starlight bending during an eclipse, refused to accept that a star could ever trap itself in such a manner. He famously quipped that there should be a law of nature to prevent a star from behaving in so bizarre a fashion. To many scientists of that era, the notion of a dark star swallowing its own light seemed like mere speculation rather than a plausible reality. In the 1930s, however, a young Indian astrophysicist named Subrahmanyan Chandrasekhar dug deeper into the fate of dying stars. In 1930, at just 19 years old, Chandrasekhar computed during a sea voyage to England that there is an upper limit to how massive a white dwarf, the remnant of a burnt-out star, can be. Beyond roughly 1.4 times the mass of our Sun, he found, the pressure of electrons inside a star's matter would no longer be able to support the star against gravity. A star heavier than that, once its nuclear fuel was exhausted, would be unable to hold itself up as a white dwarf. It would have to collapse further. When Chandrasekhar presented this result in the early 1930s, it was met with skepticism and even hostility. The eminent Arthur Eddington, in a public debate in 1935, ridiculed the idea that nature would allow such a catastrophic collapse. He essentially dismissed Chandrasekhar's conclusion as a reductio ad absurdum, an absurd result that must indicate a flaw in the reasoning. Under the weight of Eddington's authority, Chandrasekhar's prediction was largely ignored at the time. It would take decades and new developments in physics for the significance of his work to be fully recognized. It had in fact laid the groundwork for understanding how black holes could form. Meanwhile, in 1939, physicists J. Robert Oppenheimer and Hartland Snyder took the concept further in a groundbreaking calculation. They modeled the final collapse of a massive star and showed that, in principle, nothing could stop it from forming a black hole. In their idealized model, an outside observer would see the star's surface slow and freeze as it approached the critical radius, while the infalling matter itself continued inward to create a hidden singularity. This work was essentially the first modern description of black hole formation on paper. Yet this remarkable insight arrived at an inopportune time. World War II was on the horizon, and Oppenheimer soon shifted his focus to wartime projects. The 1939 black hole study gained little notice and was largely forgotten for a while. The concept of completely collapsed stars slipped into obscurity, treated as a theoretical footnote rather than a pressing astrophysical reality. For about 2 decades, black holes were rarely mentioned. They lingered as a minor curiosity in theoretical physics. Then, in the early 1960s, interest in these dark objects was dramatically revived by new discoveries in the cosmos. In 1963, astronomers identified the first quasar, an incredibly bright and distant beacon at the core of a galaxy, outshining entire galaxies. Its energy output was so vast that conventional explanations faltered. One compelling idea was that it was powered by a supermassive black hole devouring matter at the galaxy's center. Around the same time, other breakthroughs occurred that lent new credibility to the black hole concept. In 1965, British theorist Roger Penrose published a rigorous proof that under very general conditions, if an object collapsed beyond a certain point, it would inevitably form a singularity and an enclosing event horizon, essentially confirming that black holes are a natural outcome of Einstein's theory. And in 1967, astronomer Jocelyn Bell discovered the first pulsar, a rapidly spinning neutron star. The existence of such ultra-dense neutron stars, just one step short of a black hole, showed that nature was indeed capable of producing extreme remnants of stars. These developments nudged black holes from a theoretical abstraction toward a plausible reality. In 1967, American physicist John Archibald Wheeler coined the term black hole during a conference, giving a memorable name to these gravitational dark objects. The name stuck and helped to popularize the concept. By the early 1970s, attitudes had shifted. Black holes were increasingly accepted as real astrophysical entities, not just mathematical oddities. Evidence was mounting. X-ray astronomy was revealing mysterious high-energy sources in our galaxy that hinted at hidden massive objects. One famous example was Cygnus X1, identified in the early 1970s in the constellation Cygnus. This intense X-ray source turned out to be a binary system, a bright blue supergiant star orbiting an unseen companion. The invisible object had a mass several times that of the Sun, yet it emitted no light, exactly what one would expect for a black hole. Matter from the blue star was being pulled toward the dark companion, heating up and emitting X-rays just before plunging past its event horizon. The evidence for this unseen object became so strong that even prominent skeptics had to concede. Stephen Hawking famously lost a friendly bet that Cygnus X1 would turn out not to be a black hole. Discoveries like this provided some of the first strong observational evidence that black holes truly exist. The reluctance was giving way to awe and curiosity. Black holes, which once provoked disbelief, were increasingly acknowledged as fundamental components of the universe. They offered explanations for cosmic puzzles and became targets for new observations. By the end of the 20th century, black holes were a central subject of astrophysics. From stellar mass black holes born in supernovae to the gargantuan black holes anchoring distant galaxies, the journey from doubt to acceptance was essentially complete. What began as Einstein's uncomfortable prediction had become an empirical reality supported by multiple lines of evidence. Black holes had secured their place in our cosmic menagerie as fundamental and fascinating denizens of the universe. With black holes now firmly acknowledged as real, scientists turned to the question of how nature actually produces these gravitational enigmas. The most common pathway, it turns out, is through the violent death of massive stars. Throughout a star's life, there is a beautiful balance at play. Gravity pulls the star's mass inward, while pressure from nuclear fusion in the core pushes outward. For millions, or even billions of years, a massive star maintains this delicate equilibrium, shining steadily as it burns its nuclear fuel. Eventually, however, the fuel in the star's core is exhausted. When a massive star reaches that point, the outward pressure dies away, and gravity suddenly gains the upper hand. In a matter of seconds, the core of the star collapses inward. The star's heart, once a roaring furnace, caves in under its own weight, and the stage is set for a dramatic end. In a star perhaps 10 or 20 times the Sun's mass, this final collapse is cataclysmic. The core implodes and heats up to incredible temperatures as it is squeezed by gravity's unforgiving grip. Within a fraction of a second, the core can go from the size of the Earth to just a few tens of kilometers across. When it can compress no further, the collapsing core rebounds slightly, sending a powerful shockwave racing outward. This shockwave shreds the star's outer layers in a titanic blast. The star goes supernova, a cosmic explosion so brilliant it can outshine an entire galaxy for a short time. For weeks, the dying star pours out more light than billions of normal stars combined. In that violent fireball, the star's material is blown into space, and new heavy elements are forged in the process. The supernova marks the spectacular death of the star. But even as the outer layers erupt into the void, something profound is happening in the collapsed core. It is here that a black hole may be taking shape. After the supernova's outward fury, we are left with the fate of the collapsed core itself. If the core was not very massive, below a certain threshold, perhaps around 2 to 3 times the Sun's mass, the collapse may halt at an intermediate stage. In that case, the core becomes a neutron star, an ultra-dense ball made mostly of neutrons, unimaginably dense. A single teaspoon of neutron star material would weigh billions of tons on Earth. A neutron star packs the mass of a sun into a sphere only about 10 kilometers across, and it is an astonishing object in its own right. But it still retains an identity in our universe. It has a surface. It can be observed, as a pulsar, for instance. However, if the core of the star is more massive than that critical threshold, even the immense pressure of neutron degeneracy, the quantum forces, resisting further squeezing of neutrons, cannot hold it up. With nothing left to counteract gravity, the core's collapse resumes inexorably. Within a fraction of a second, it contracts beyond any definable surface. It effectively vanishes behind an emerging event horizon, crossing the point of no return. In that instant, a black hole is born. What was once the heart of a star becomes a gravitational trap. The mass, still present, now resides in a radically different form, in a singularity wrapped in darkness. The birth of a black hole is an oddly silent affair, cloaked by the roar of the supernova around it. As we just described, the outer layers of the star explode outward in a dazzling display of light and energy. But deep inside, the core's transformation into a black hole makes no sound and emits no light of its own. When the brilliance of the explosion fades, what remains at the center is invisible. The once mighty star has left behind an object smaller than a city, yet with a gravitational pull so intense that nothing can escape it. In the aftermath, that central region of space is marked only by the gravitational influence of the new black hole. If we look at the debris of the supernova spreading into space, we might see a faint nebula or expanding cloud. But the core is gone from view, replaced by a gravitational footprint on the fabric of spacetime, a patch of darkness that will pull on anything that strays too close. Although the black hole itself is dark, it can reveal its presence indirectly through its effects on the surroundings. In the wake of a supernova, the newborn black hole might find itself near leftover gas, or maybe even in a binary system with another star, if the original star had a companion. Gas that falls toward the black hole will swirl into an accretion disk, heating up from friction and gravitational energy. That disk of infalling material can shine intensely, often in X-rays or other high-energy light, as the gas spirals inwards and gets compressed and heated. We cannot see the black hole's surface, it has none, but we can see the last flash of light from matter as it orbits just outside the event horizon before plunging in. In a binary system, the black hole's gravity can strip gas from the companion star, siphoning it into this hot whirlpool and creating a persistent X-ray source. By observing such X-ray signals and the wobbling motion of the visible companion star, astronomers can infer the hidden black hole's presence. This is exactly how Cygnus X1 and similar systems gave themselves away. Stellar collapse is the primary way black holes form. But it is not the only path. In regions of space where matter is exceptionally dense, black holes can emerge through other exotic routes. In the crowded cores of star clusters, for example, stars can collide or merge together. If two massive stars merge, their combined mass might push the product over the collapse threshold, resulting in a black hole that neither star alone could have produced. In close binary systems, one star can transfer mass onto another dead core, say, feeding a neutron star until it gains enough mass to collapse into a black hole. Even on a larger cosmic scale, black holes may sometimes form by a more direct route. In the early universe, immense clouds of gas could have collapsed directly under their own gravity, without first fragmenting into stars. Such a process would create primordial black holes, which could serve as seeds that later grow into the supermassive black holes in galactic centers. Across all these scenarios, the essential theme is the same. When too much mass is packed into too small a space, gravity triumphs completely, and a black hole takes shape. Let's return for a moment to the very first stars that illuminated the universe. These stars, born not long after the Big Bang, were forged from nearly pure hydrogen and helium, and without heavier elements to cool the gas, they grew far larger than most stars today. Some of those primordial stars may have been hundreds of times the Sun's mass. They burned their fuel at a ferocious rate, living short, brilliant lives and ending in catastrophic collapses. Many of the first stars likely died as black holes, seeding the early universe with a first generation of these dark objects. Those initial black holes, born in an infant universe, did not remain solitary. As the first galaxies took shape, these black holes could merge with one another, or consume surrounding gas, growing into more massive black holes. We observe extremely bright quasars in the distant universe, when it was less than 1 billion years old, that are powered by black holes billions of times the Sun's mass. The presence of such massive black holes so early in cosmic history suggests they had a head start. It's possible that the deaths of the very first stars and the direct collapse of primordial gas clouds provided that head start, seeding the cosmos with black holes that would later grow into the supermassive giants at galaxy centers. With an understanding of how black holes form, the next challenge is to find them in the universe and study their strange properties. By their very nature, black holes emit no light, hiding behind their event horizons. But astronomers have learned to detect them indirectly and even capture images of their shadows. As we continue our exploration, we will follow the scientists who hunted for evidence of black holes and delve into the remarkable techniques and discoveries that have brought these dark mysteries into the light of observation. The enigma of the black hole, caught in the grip of its own gravity, continues to draw us in, deeper into understanding and wonder, drawing us toward the very edge of the knowable universe. In the stillness of deep space, a colossal star is living out its final act. For millions of years, it has blazed with fierce light, forging heavier elements in its core and illuminating its corner of the galaxy. But even the brightest stars cannot burn forever. This particular giant, perhaps 20 times more massive than our Sun, has reached a critical threshold. Its heart has filled with the ash of its nuclear fire, elements like iron, which can no longer fuel the star's fusion furnace. With each passing year, the outward pressure that once balanced gravity begins to falter. Inside the star's core, creation is turning into destruction. For eons, hydrogen fused into helium at the center, releasing the energy that made the star shine. As the star aged, it burned through successively heavier fuels. Helium fused into carbon and oxygen, then into neon, magnesium, and silicon. Each stage burned faster than the last. What a modest star might consume over billions of years, this titan devours in a few million. Now the process has reached its limit. The core is packed with iron, an element that yields no energy when it fuses. In fact, fusing iron actually consumes energy. It is as if the star's life force has been poisoned by its own exhaust. No more fuel remains to counteract gravity's pull. The balance that sustained the star for ages is tipping, inexorably, toward collapse. This fate is sealed for any star above a certain size. Even Betelgeuse, the red supergiant that gleams in Orion's shoulder, is living on borrowed time at only about 10 million years old. It has swollen to enormous proportions, and its core is running low on viable fuel. In the cosmic blink of an eye, perhaps tomorrow, perhaps 100,000 years from now, Betelgeuse will succumb to the same destiny our giant star now faces. Gravity will win, and collapse will begin. When the end comes, it comes swiftly and without mercy. In the span of less than a heartbeat, the star's iron core caves in under its own titanic weight. One moment, it is a sphere perhaps the size of Earth, broiling at tens of millions of degrees. The next moment it is plunging inward, compressing further and further, faster and faster. Temperatures in the core spike to unimaginable levels, tens of billions of degrees. Atomic nuclei are crushed together beyond anything normal matter can withstand. A flood of neutrinos, ghostly subatomic particles, bursts out from the core and streams through the star as gravity pulls the outer layers inward. The mighty star, so huge just moments before, is literally imploding. Then, abruptly, there is a rebound. The core's collapse grinds to a halt as matter reaches nuclear densities and stiffens like a compressed spring. In an instant, the core bounces back outward slightly. This tiny, sudden expansion is enough to launch a shockwave. That shock races outward from the core into the infalling stellar material. It's as though the star is exploding from the inside out. A titanic blast is now set in motion deep within the dying star. The stellar endgame has reached its climax, and the next act will be one of almost unfathomable violence. A split second later, the star erupts as a supernova. A tremendous explosion rips through its layers, tearing the star apart from within. In that instant, our once steady giant becomes a beacon so brilliant it can outshine an entire galaxy. The night sky of any nearby worlds would suddenly flood with this fierce light, as bright as a billion suns. The supernova's flash and fury are the grand finale of the star's life, dominating the cosmic landscape for a brief time before gradually fading. Shockwaves blast the star's outer gases into space, and a beautiful but expanding cloud of stellar debris begins to form around the detonation site. This cosmic blast is more than just destruction. It is also creation. In the furnace of the explosion, lighter elements are smashed together into heavier ones. Gold, silver, iodine, uranium. Countless rare elements are forged in the supernova's fiery crucible. These newly minted atoms, along with the elements the star produced over its lifetime, are hurled outward into the galaxy. They will drift through space for eons, mixing with clouds of gas and dust. Someday, that enriched material may collapse into new stars and new planets. In fact, the iron in your blood and the calcium in your bones were once forged in a supernova that exploded before the sun was born. In death, the star gives back to the cosmos, seeding the future with the ingredients of life and worlds to come. At the heart of the chaos, the star's core has undergone a profound transformation. All the while that the star's outer layers were blowing themselves to shreds, the core was collapsing into an extraordinarily compact object. For a star of this mass, there are two possible outcomes to this collapse: a neutron star or a black hole. If the core is relatively small, below a certain critical mass, it crushes down to form a neutron star. This is an object so dense that atoms cannot survive. Protons and electrons are squeezed together to become neutrons. A neutron star packs the mass of 500,000 Earths into a sphere only a dozen miles across. It's as if an entire sun were compressed into a city. But if the core is any heavier, roughly more than 2 or 3 times the mass of our Sun, then nothing can halt the collapse. Not even the degeneracy pressure holding up a neutron star can withstand that weight. In that case, the core continues to implode until it vanishes behind an event horizon. In that violent instant, a black hole is born. The supernova, then, is a kind of cosmic gateway. On one side of it, we have a massive star. On the other side, after the blast, we have something entirely new. Through the supernova's fury, the universe transforms the star's core into one of the densest forms of matter known, a newborn neutron star, or, in the more extreme case, a black hole. To an outside observer, this newborn black hole would be invisible, hidden behind the glare of the supernova's expanding debris. For a time, all we might see is the blossoming cloud of hot gas rushing outward. But deep in the center, the dark core remains, a black hole lurking silently, an object with no surface and no light, born from complete collapse. Not every massive star announces its death with such a flamboyant display. Astronomers have found hints that some colossal stars might skip the supernova spectacle altogether. Instead of a brilliant explosion, these stars quietly collapse in on themselves and simply disappear from view. A failed supernova. One moment a star shines normally, the next it fades and is gone, as if swallowed by the darkness. In these cases, it's thought that the core implosion proceeds directly into forming a black hole, and most of the star just falls in after it. The universe, in effect, allows a black hole to materialize without the fireworks, just a silent collapse, perhaps marked only by a faint whisper of neutrinos or a subtle burst of ghostly gravitational energy. Whether by a dramatic explosion or a quiet collapse, the end result for a sufficiently massive star is the creation of a black hole. It is the ultimate transformation. Matter that once shone brightly as a sun is now packed into an infinitely deep gravitational well. In some instances, the birth of a black hole might even announce itself with an extraordinarily intense yet fleeting signal. Astronomers have observed mysterious flashes of high-energy gamma rays, the so-called long gamma-ray bursts, coming from distant galaxies. These bursts last only seconds, but release more energy than the sun will emit in its entire lifetime. Many scientists believe this is the birth cry of a black hole. The moment a massive star's core collapses and a black hole forms, jets of energy blast out from the dying star's poles, heralding the arrival of a new black hole, even as the rest of the star is swallowed into darkness. Now the stellar explosion has passed. The once mighty star has shredded itself into an expanding nebula of glowing debris. At its center lies the crushed core, a hyperdense neutron star, or, if the star was massive enough, a newborn black hole. Let us follow the latter path. Imagine peering into the aftermath. Swirling clouds of expelled gas, cooling and glowing faintly with radioactive afterlight, and in the middle, unseen but present, a gravitational phantom. For now, the black hole might simply sit in the center of the wreckage, like an invisible ember at the heart of a fading fire. But its story is far from over. Drawn by the black hole's immense gravity, some of the ejected material, and any nearby gas that wanders too close, will begin to fall back inward. The black hole's feast is about to begin, and with it will come new light. Paradoxically, this darkness is about to announce itself. The quiet interlude after the explosion is ending, and the dance of accretion is about to commence. The black hole that remains after the star's death may be invisible at first, but it soon makes its presence known through the fate of any matter that strays too close. In the aftermath of the supernova, gas and stellar debris feel the pull of this dark, new gravity well. Rather than plunging straight in, the infalling material spirals around the black hole, drawn in as if caught in a whirlpool. A disk of gas and dust forms, swirling faster and faster as it settles into orbit. This is the accretion disk, a cosmic maelstrom of matter orbiting an object that will eventually consume it. The particles in the disk rub against each other as they circle at immense speeds. Friction and compression heat the gas to incredible temperatures, causing it to glow brilliantly. What was once cold, dark, interstellar material is now a radiant platter of light encircling a void at the center. Up close, this disk would be an awe-inspiring sight. Imagine a glowing whirlpool around a black pit. The gas shines in hues of ultraviolet and X-ray. So intense is its heat. As the gas spirals inward, it whips around at a significant fraction of the speed of light near the disk's inner edge. The innermost regions blaze white-hot, while the outer parts of the disk are cooler and reddish. If we could hover nearby, we would see the disk as a flattened halo, perhaps with one side appearing brighter than the other. That brighter side is where gas is moving toward us, its light boosted in energy. The opposite side, moving away, looks dimmer. This strange asymmetry results from the disk's dizzying rotation and the effects of relativity. The black hole's gravitational field also twists the path of light around it, so from some angles we might even see the far side of the disk strangely warped above and below the black hole. A funhouse mirror view created by gravity's lens. The entire scene is both beautiful and eerie. A brilliant, thin disk hanging in the blackness of space, light whirling into darkness. Within the accretion disk, chaos and order coexist. The gas orbits in relatively orderly planes, yet turbulent eddies and magnetic storms rage within it. The closer the material gets to the black hole, the more violent and unpredictable the environment becomes. At a certain point, extremely close to the black hole, the orbiting gas becomes so hot and energized that it forms a roiling corona above and below the disk, a halo of superheated plasma. Random flares and X-ray flashes spark from this seething region, the result of magnetic fields tangling and snapping like overstressed rubber bands. These flares can momentarily flood space with high-energy radiation, a signal that something extreme is happening just outside the point of no return. Remarkably, even as the accretion disk shines brightly, the black hole itself remains utterly dark. It is the ultimate paradox. The black hole forces matter to emit light and radiation as it falls in. Yet if that matter crosses a certain invisible boundary, all the light vanishes. This boundary is the event horizon, the edge beyond which nothing can escape. As the spiraling matter inches closer to this threshold, it glows fiercely, running its final laps around the black hole. Then, in a final plunge, each parcel of gas slips past the event horizon and is never seen again. To an outside observer, the infalling matter appears to slow and dim as it approaches the horizon. Its light stretched to longer and longer wavelengths until it fades away. What was a lively, luminous dance ends in sudden silence as matter makes that one-way trip into the black hole's grip. Not all the matter in the disk will succumb to that fate immediately. Black holes are messy eaters. Some of the inflowing material never reaches the event horizon at all. Twisted by magnetic fields and jolted by internal shocks, a fraction of the gas is redirected and hurled away from the disk's center. In a spectacular feat of astrophysical engineering, twin jets of particles can erupt from just outside the black hole, shooting out along the north and south poles of the disk. These jets are like enormous cosmic blowtorches, composed of matter accelerated to nearly the speed of light. They pierce out of the surrounding nebula, carrying away energy and angular momentum. In the case of a stellar mass black hole, the jets might span only a few light years, but for the supermassive black holes in galactic cores, they can reach hundreds of thousands of light years into space, drilling into intergalactic medium. The exact mechanism that launches these jets remains something of a mystery. It likely involves magnetic field lines wound tight by the spinning disk and black hole, flinging some inflowing particles back out. But whatever the cause, the result is stunning. Even as a black hole devours material, it can also propel narrow beams of it outward, broadcasting its presence far across the cosmos. The energy released in the accretion process can be tremendous. As matter falls toward a black hole and heats up, it converts gravitational energy into radiation with astonishing efficiency. In fact, accretion onto a black hole is one of the most efficient energy-releasing mechanisms known, far surpassing the energy per pound that nuclear fusion produces in normal stars. Only a small fraction of the infalling mass needs to be converted to light to power some of the brightest objects in the universe. A cupful of matter spiraling into a black hole could outshine a star, albeit briefly, if all its energy were released as radiation. In our scenario of a stellar black hole feeding on the debris of a supernova, the luminosity might be enormous for a time. Across the galaxy, X-ray telescopes would pick up the flickering beacon of this accretion disk, announcing the black hole's presence. Long before anyone could hope to see the black hole directly, its glowing dinner plate of infalling gas would give it away. In many ways, a feeding stellar mass black hole is a miniature version of the energetic phenomena we see on a much larger scale in galactic nuclei. The same basic dance occurs across a vast range of masses. On the small end, a black hole a few times the Sun's mass can pull gas from a companion star, creating a bright X-ray source that astronomers dub a microquasar. On the giant end, supermassive black holes, millions or billions of times the Sun's mass, draw in gas and blaze as quasars, beacons visible across the universe. The physics is fundamentally similar. Gravity's inexorable pull forces matter to dance a final dance, shedding energy as light before succumbing to darkness. It is a choreography written by gravity and thermodynamics, a universal script that plays out wherever black holes and abundant matter meet. Our newborn black hole, once a hidden remnant of a supernova, has now revealed itself through this accretion dance. Over time, as it consumes the available gas and dust around it, the spectacle will wane. The disk will thin out as the black hole empties its immediate surroundings, and the great light show will gradually fade. If the black hole exhausts its fuel supply, it will become quiescent and dark again, perhaps drifting silently through space as an invisible phantom. Yet even then, it remains ready to flare back to life if new material crosses its path. A black hole can wake up from dormancy after millions of years of quiet, simply by encountering a fresh cloud of gas or a stray star to feed on. Then the dance of accretion will resume, and the black hole will once again cloak itself in a luminous, swirling gown of matter. Up to now, we have followed the journey of a black hole's birth and feeding in theory, but how did we humans come to realize that such exotic objects truly exist in the universe? For a long time, black holes were considered speculative, theoretical ghosts predicted by mathematics, with no proof in hand. By their very nature, they emit no light of their own, and many scientists doubted we would ever find concrete evidence of them. And yet, the spectacle of accretion provides a way for black holes to be indirectly seen. The X-rays and other energetic radiation unleashed by matter spiraling into a black hole do not stay bound to the darkness. They stream out across space, carrying a whisper of the black hole's presence to anyone with the instruments to listen. By the mid-20th century, our technology had finally advanced enough to catch these whispers. In the 1960s, rockets and satellites lifted X-ray detectors above Earth's atmosphere, allowing astronomers to probe the high-energy sky for the first time. Almost immediately, they discovered mysterious X-ray beacons in the cosmos, sources far brighter in X-rays than any normal star. These were puzzling at first, invisible objects announcing themselves only through powerful X-ray emission. One by one, scientists pieced together the clues. Many of these X-ray sources turned out to be coming from binary star systems, pairs of stars in which one star was unseen, yet incredibly massive. The visible star seemed to orbit an invisible partner, and that partner was drawing gas from it, heating the gas into an X-ray emitting disk. It was exactly the scenario we've imagined. A black hole quietly siphoning material from a companion star and radiating X-rays as a result. At long last, the theoretical had become real. Those faint, distant X-ray signals were the first strong evidence that black holes were not just figments of theory, but actual cosmic inhabitants. They were the gentle whispers that finally confirmed we were indeed caught in a black hole's grip. It was one thing to imagine these X-ray emitting disks in theory. It was another to detect them in reality. Before the 1960s, astronomers had never seen the sky in X-rays at all. Our atmosphere mercifully blocks X-ray radiation, which protects life on Earth, but hid the high-energy universe from our view. That changed with the dawn of the space age. In 1962, a team of scientists lofted a simple Geiger counter on a suborbital rocket above the atmosphere, aiming it at the heavens. To their surprise, the instrument picked up a strong X-ray signal from somewhere in the constellation Scorpius. This was the first discovery of a cosmic X-ray source, later named Scorpius X1. It turned out not to be a black hole at all, but a neutron star voraciously devouring gas from a nearby companion. Still, it was proof that fantastically energetic phenomena were out there, invisible to optical telescopes, yet shouting in X-rays. This success kicked off the age of X-ray astronomy. Dedicated space observatories soon scanned the skies, and the once dark, high-energy universe came to life with discoveries. One of those discoveries became the first widely accepted black hole. In the early 1970s, data from the Uhuru X-ray satellite revealed a particularly intriguing source of X-rays in the constellation Cygnus. It was dubbed Cygnus X1, the first X-ray source detected in Cygnus. Astronomers noticed that this source flickered and fluctuated rapidly, a clue that the X-rays came from a very compact region. Moreover, they identified a bright blue supergiant star at the same position, orbiting an unseen companion. Two independent teams, one in England, led by Louise Webster and Paul Murdin, and one in Canada, led by Tom Bolton, studied the visible star's motion and in 1971 concluded that its invisible partner had a mass on the order of 10 suns. An object that massive, yet producing no visible light and confined to such a small region, could only be one thing: a black hole. Cygnus X1 thus became the first strong black hole candidate in our Milky Way. At first, the claim of a black hole in Cygnus X1 was met with caution, even skepticism. The idea of an actual black hole, this term had only been popularized a few years earlier, still felt like science fiction to many. Renowned physicist Stephen Hawking was initially doubtful and even made a playful bet in 1975 with fellow physicist Kip Thorne. Hawking wagered that Cygnus X1 was not a black hole. By his own admission, Hawking said he bet against it partly as insurance. If it wasn't a black hole, at least he'd win the bet. But as observations piled up, the evidence for Cygnus X1 grew overwhelming. No other explanation fit the data. The X-rays from Cygnus X1 flared and faded in ways consistent with hot gas plunging into a deep gravitational well. The companion star, a huge luminous blue star, was clearly losing matter, a stream of gas being pulled off its surface into an accretion disk around the unseen mass. By the late 1980s, Hawking conceded the bet, acknowledging that Cygnus X1 was almost certainly a black hole. The unseen companion was unseen no more, at least not to the discerning eyes of science. We had heard its whispers and learned to understand what they meant. Cygnus X1 was just the beginning. In the decades that followed, astronomers found dozens of similar systems. Binary stars, where one component is a normal star and the other is a hidden, heavy black hole. Each discovery told a similar story in X-ray whispers. Gas stolen from a visible star swirls into an invisible core, releasing X-ray light as it is heated and consumed. Some systems showed sudden X-ray bursts or quasi-periodic oscillations, flickering patterns that gave insight into the behavior of matter just outside the event horizon. A few, like an object charmingly named GRS 1915 plus 105, exhibited astonishing variability, including sudden X-ray and radio outbursts, as if chunks of its accretion disk were being flung outward. These were dubbed microquasars because they mimicked, on a smaller scale, the powerful quasars found in distant galaxies, which are powered by supermassive black holes. Piece by piece, the case for black holes grew stronger. Not only did they exist, but the exotic processes scientists envisioned around them, accretion disks, relativistic jets, intense X-ray emission, were truly occurring and could be observed. To the public, black holes quickly went from obscure theory to headline news. Here were objects so strange that not even light could escape them. Yet astronomers had found ways to detect their presence. People heard that a black hole had been discovered in some constellation, and imaginations ran wild at the concept. In reality, what had been found were those telltale X-rays from matter in a black hole's grip. It took careful deduction to go from the data to the conclusion of a black hole, but eventually, nearly everyone was convinced. By the 1990s, the existence of stellar mass black holes in our galaxy was widely accepted. Black holes had graduated from mathematical oddities to concrete astrophysical entities, thanks largely to those early X-ray whispers that betrayed their existence. Even today, these X-ray binaries remain one of the primary ways we find stellar black holes. Astronomers continue to discover new examples, sometimes when a long quiet black hole in a binary system wakes up and starts feeding again, suddenly brightening in X-rays. We now suspect that the Milky Way is teeming with black holes, tens of millions of them, though the vast majority are quiet and hidden. Only when one has a close companion, or happens to capture some stray gas, do we get a glimpse of it. Each one we detect is like hearing the faint echo of a cosmic beast stirring in its lair. The early clues were subtle and required ingenuity to decode. Astronomers had to rely on indirect evidence, the wobble of a visible star, the timing of X-ray pulses, the spectrum of high-energy light, all to infer the presence of an object that by itself could not be seen. It's a bit like inferring the presence of wind by watching leaves rustle. The black hole itself was the unseen wind, and the X-rays were the rustling leaves. By such methods, humanity finally confirmed that nature's idea of a black hole was not just a theoretical fancy. Black holes were as real as the stars that orbit them. With the existence of stellar black holes firmly established, a new question loomed. Were these merely rare, peculiar objects, or the small cousins of something even more formidable? Even as researchers studied the stellar mass black holes in our galactic neighborhood, evidence was emerging that the universe harbors black holes on vastly different scales. The whispers that revealed Cygnus X1 were soon joined by other clues coming from the hearts of distant galaxies and the early cosmos, hinting at an entirely new category of black holes, millions or billions of times the mass of the Sun. The hunt for black holes was about to expand far beyond the Milky Way binaries, leading us into the realm of the truly colossal. Stellar mass black holes, weighing a few to a few dozen suns, are only one tier of a much grander cosmic hierarchy. Astronomers began to suspect that nature makes black holes on far larger scales. In 1963, astronomer Martin Schmidt identified the first quasar, an almost star-like point of light that turned out to be the extremely distant core of a galaxy, shining with unbelievable brilliance. To produce so much energy from such a compact region, theorists proposed a supermassive black hole as the engine, a black hole millions or billions of times the Sun's mass, devouring matter and converting it to light. This was a radical leap at the time, a black hole not of 10 suns, but of 10 million suns. Yet quasars provided the first strong hint that black holes come in a spectrum of sizes, and that some can grow into light-devouring leviathans. Between the stellar and the supermassive lies a middle ground that has long intrigued scientists: intermediate mass black holes. Could there exist black holes weighing a few hundred or a few thousand suns, heavier than any single star's remnant, but far lighter than the monsters in galactic cores? For decades, intermediate black holes remained hypothetical. They would be too massive to form from an ordinary supernova, yet too small to power a quasar, making them tricky to detect. Still, a few tantalizing clues have surfaced. In certain globular clusters, spherical groups of old stars, astronomers have observed stars moving as if a dark mass of perhaps thousands of suns lurks at the cluster's center. And some unusual X-ray sources, called ultraluminous X-ray sources, shine so intensely that a stellar mass black hole accreting gas seems insufficient to explain them. These objects might be powered by intermediate mass black holes, just big enough to pump out more energy than a smaller black hole could. The evidence is not yet conclusive, but many suspect that intermediate mass black holes are out there, perhaps as the missing links in black hole evolution. After all, how do you jump from a 10 solar mass black hole to a billion solar mass black hole without something in between? Nature may build its giants step by step. We've learned that black holes grow. A black hole is not a static, unchanging thing. It can gain mass over time by consuming matter or merging with other black holes. Every meal a black hole eats, every star, gas cloud, or stray particle it pulls in adds to its gravitational bulk. Given enough food and enough time, a black hole can swell from modest beginnings to enormous proportions. In the dense environments of young galaxies and star clusters, black holes may even meet and merge with one another. Imagine a cluster where several massive stars each leave behind a black hole. These black holes sink to the cluster's center and eventually coalesce into a larger one. Two become one, then engulf another, and so on, step by step, building a significantly more massive black hole. In the modern universe, such events are rare. In the much younger universe, however, they were likely more common, seeding the growth of supermassive black holes. A stunning confirmation of black holes' growth through mergers came in 2015. In that year, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected an exceedingly subtle ripple passing through Earth. a disturbance in space-time itself. These ripples were gravitational waves emanating from the merger of two black holes in a distant galaxy. Each black hole was around 30 times the mass of the Sun, larger than any stellar black hole previously identified through X-rays. As they spiraled together and merged, they released an enormous burst of energy, not in light, but in the form of vibrations in space-time, literally shaking the fabric of the universe like a pond rippling after a stone's throw. For a brief moment, the power output in gravitational waves exceeded the light from all the stars in the observable universe. LIGO's instruments picked up the telltale chirp of this event, the rising tone produced as the two black holes whirled faster and faster before colliding and coalescing into one. This was humanity's first direct sound of black holes merging. It not only confirmed a key prediction of Einstein's general relativity, but also revealed a new way to detect black holes that emit no light at all. Through gravitational waves, we suddenly had ears on a previously silent realm of the cosmos. And what we heard immediately told us that black holes can indeed grow by smashing together. The final black hole formed in that distant collision was about 60 solar masses, slightly less than the sum of its parents, because a portion of their mass was converted to the energy of the gravitational waves, as predicted by E equals mc squared. We had witnessed, for the first time, black holes in the act of becoming a single, more massive one. In subsequent years, gravitational wave observatories have caught many more such mergers. Some involved black holes of 20 or 30 solar masses. Others involved heavier black holes merging to form objects of 100 solar masses or more. One event in particular hinted at the birth of a black hole around 150 times the Sun's mass, squarely in that intermediate range, resulting from a collision. These observations are quickly filling in what was once an empty middle of the black hole mass spectrum, suggesting that intermediate black holes do form when conditions allow. We are also learning that black holes can spin at tremendous rates, and that when they merge, they can send recoiling vibrations through space-time. It's a dynamic, violent portrait, but it's how nature builds some of its heftiest black holes, by crashing smaller ones together to make bigger ones. While stellar black holes are born in the present universe through supernovae, the truly massive black holes trace their origins to much earlier times. The universe's first generations of stars, which formed when it was only a few 100 million years old, may have been titans themselves, hundreds of solar masses each. When those primordial giants ran out of fuel, they likely collapsed directly, perhaps forming black holes of 100 solar masses or more in one go. These could serve as the seeds for the supermassive black holes that came later. If a seed black hole found itself in the dense core of a young galaxy, it could rapidly swallow gas from its surroundings. With abundant fuel, its mass would balloon. Calculations show that a black hole can grow at an exponential rate if it continuously accretes gas at the maximal allowed pace, a rate limited by a balance of outward radiation pressure, known as the Eddington limit. Still, there's a cosmic puzzle. We observe quasars so distant that their light began its journey when the universe was less than 1 billion years old. Yet some of these quasars already harbour black holes of several billion solar masses. How could something grow that big, that fast? It remains one of the fascinating mysteries in black hole astrophysics. Perhaps those early seed black holes were unexpectedly massive to begin with. Or maybe they experienced periods of super Eddington growth, gorging themselves at rates above the usual limits. One way or another, by the time the universe was 1/10 of its current age, it already contained monsters. And monsters they are. Consider the numbers. A black hole of 1 billion suns is not 1 billion times larger in physical size than a stellar black hole, but its event horizon, the boundary beyond which nothing escapes, would span a region roughly the size of our solar system. Yet this colossal object sits at the center of a galaxy that's hundreds of thousands of light years across. It's like a marble of darkness, weighing more than all the visible stars and gas around it. Supermassive black holes are relatively small in volume compared to their host galaxies, but they pack a tremendous punch. Their gravity can grip stars thousands of light years away. When they actively accrete matter, they can blaze as the brightest objects in the universe. Indeed, a quasar powered by a supermassive black hole can outshine all the billions of stars in its host galaxy combined. These cosmic giants are the hearts of active galaxies, the engines driving powerful radio jets and energetic outflows, and they appear to play a pivotal role in their galaxy's evolution, regulating perhaps the growth of stars by blasting out energy that can heat or expel the galaxy's gas. On the opposite extreme of scale, one might wonder, are there black holes even smaller than those made by stars? Could nature produce tiny black holes, say, the mass of a mountain or an asteroid? According to general relativity, it's theoretically possible for micro black holes to form under extraordinary densities, but no known astrophysical process today would create them. Some cosmologists have speculated that in the high-pressure cauldron of the Big Bang, minuscule black holes might have popped into existence. These hypothetical primordial black holes could range from masses of a large asteroid down to much smaller sizes, and the tiniest of them might have evaporated over billions of years via a slow trickle of particles known as Hawking radiation. So far, however, no evidence of such tiny black holes has been found. If they exist at all, they remain purely in the realm of speculation. Thus, the smallest confirmed black holes are still the ones born from collapsing stars, and the largest are the giants we see in galactic cores. The spectrum of black holes, from micro to mega, reveals a universe remarkably adept at producing gravity's ultimate triumph on all scales. Each type of black hole adds another piece to the cosmic puzzle. And intriguingly, all these black holes, whatever their mass, share common characteristics described by elegant equations. In the end, as physicist John Wheeler once remarked, black holes have no hair, meaning they are defined only by a few basic properties: mass, spin, and, if they carry any, electric charge. A rotating black hole 1,000,000 times the sun's mass isn't fundamentally different from one that's 10 times the sun's mass. It's just a vastly scaled-up version of the same phenomenon. As scientists recognized this kinship across scales, a profound insight emerged. Supermassive black holes and their host galaxies are interconnected. Observations revealed that the mass of a galaxy's central black hole correlates with the properties of the galaxy's bulge of stars. Somehow, the formation and growth of a galaxy and the growth of its central black hole go hand in hand, a cosmic partnership still being unraveled. It seems that these galactic hearts can influence the evolution of their entire galaxy by the energy they release, acting as a sort of thermostat for star formation over cosmic time. For generations, the center of our own Milky Way galaxy was a place of mystery. We live about 27,000 light-years from the galactic core, and from our vantage point, thick clouds of dust block the view in visible light. But astronomers suspected something extraordinary lay hidden at the Milky Way's heart. Starting in the 1960s, clues began to accumulate. That was the era when quasi-stellar objects, quasars, in distant galaxies were identified as incredibly luminous cores powered by supermassive black holes. If other galaxies had such beasts in their centers, perhaps ours did as well, even if ours was relatively quiet. In 1969, British astrophysicist Donald Lyndon Bell hypothesized that many galaxies contain dormant quasars in their nuclei. In other words, supermassive black holes that are not currently active, just slumbering in the dark. Our Milky Way, he suggested, might harbour one. The first hint of this hidden giant came in 1974. Using radio telescopes, astronomers Bruce Ballack and Robert Brown zeroed in on a compact radio source at the Milky Way's core. It was a dim speck of radio emission in the constellation Sagittarius, coincident with the very centre of our galaxy. As a bit of whimsy, this object was named Sagittarius, a star, the asterisk signifying an excited state like that of an atom. Sagittarius. A did not budge in the sky relative to the background stars, clear evidence that it was at the galaxy's centre, not a nearby object, and it was extremely small in apparent size. It wasn't definitive proof of a black hole, but it was a compelling candidate. A mysterious, compact source, likely marking the spot of a supermassive black hole about which our entire galaxy revolves. Over the next 2 decades, Sagittarius A star was studied intensively with ever-improving techniques. Radio observations grew sharper, revealing hints of structure and occasional flares at the galactic center. Infrared observations managed to pierce through the dust and glimpse stars crowded in the central region. And those stars were not just drifting lazily, they were flying. In the 1980s, physicist Charles Townes and his colleagues measured peculiar motions of gas clouds near the core, movements that made sense only if they were responding to the gravitational pull of some enormous, unseen mass. But the definitive breakthrough came in the 1990s, thanks to 2 teams of astronomers led by Reinhard Genzel in Germany and Andrea Ghez in the United States. Using powerful new infrared telescopes and advanced imaging techniques, they began tracking individual stars near Sagittarius A star. Year after year, the positions of these stars were mapped with astonishing precision. What emerged was breathtaking. The stars were orbiting something truly massive, crammed into an incredibly tiny volume at the galactic center. One star in particular, later named S2, was observed to swing around the center along a stretched-out orbit that it completed in just 16 years, an eye blink in cosmic terms. At its closest approach, S2 passed only about 17 light-hours from the central object, roughly 3 times the distance of Pluto's orbit, and it whipped by at a staggering 3% of the speed of light. Only a tremendous concentration of mass could hold a star on such a tight, rapid leash. By analysing S2's orbit, astronomers deduced the mass of the central object, approximately 4 million suns, all confined in a space no larger than our solar system. No cluster of normal stars, no swarm of dark objects, no exotic configuration other than a black hole could pack that much mass into such a small region without either collapsing further or flying apart. The conclusion was inescapable. A supermassive black hole resides at the heart of the Milky Way. In 2020, Genzel and Ghez were awarded the Nobel Prize in Physics for this work, which decisively unveiled our galaxy's dark central mass. Our Milky Way, it turned out, is far from unique. As telescope technology improved and observations poured in, it became evident that supermassive black holes lurk in the cores of most, if not all, large galaxies. Astronomers used instruments like the Hubble Space Telescope to peer into the nuclei of nearby galaxies and measure the velocities of stars and gas swirling around their centers. Again and again, they found the telltale signature of an immense, hidden mass. The Andromeda Galaxy, our big neighbor, harbors a dark object of roughly 100 million solar masses at its core. Giant elliptical galaxies like M87 in the Virgo cluster boast central masses measured in the billions of solar masses. M87 had long been suspected to hold one of the largest black holes in the local universe. Its central region emits a jet of material shooting outward at nearly light speed for thousands of light years. evidence of a powerful engine within. By the late 1990s, surveys of galaxies systematically revealed that virtually every galaxy with a substantial bulge of stars likely has a supermassive black hole at its center. Moreover, a correlation emerged. The mass of the black hole and the collective properties of the galactic bulge, such as the velocity dispersion of its stars, seem to be linked. This suggested that the growth of the black hole and the growth of the galaxy were intimately connected. The titans in the galactic cores were not just passive inhabitants, they might be central to shaping the galaxies around them. By the early 2000s, the case was closed. Supermassive black holes were accepted as a fundamental component of the universe. Still, much of the evidence was indirect. We inferred black holes from the motion of stars and gas, from extraordinary energy output, from the presence of jets and high-energy radiation. An audacious question lingered. Could we ever see one of these behemoths directly, to observe the region right around its event horizon? For years, this goal remained in the realm of imagination. But human ingenuity pressed on, and eventually the seemingly impossible was achieved. In April 2019, the world was presented with an image that once would have been dismissed as fantasy. A lopsided ring of golden light surrounding a dark shadow, the unmistakable silhouette of a black hole's event horizon. This was the supermassive black hole in M87, captured by the Event Horizon Telescope, EHT, a global network of radio observatories acting in unison as a planet-sized telescope. We were gazing at the glowing footprint of a cosmic giant, the bright ring formed by photons whipping around the black hole, and the dark central shadow where the event horizon's gravity had captured all light. The image matched in every detail what general relativity had predicted for such a scenario. For the first time, humanity had seen the direct evidence of a black hole, witnessing light bent and captured by an abyss. Not long after, in May 2022, the EHT team released a similar achievement, even closer to home, an image of Sagittarius, a star, our own galaxy's central black hole. This feat was even more challenging. Sagittarius. A star is over 1,000 times less massive than M87's black hole, which means the matter orbiting it moves and changes appearance on timescales of mere minutes, hundreds of times faster than in M87's case. Capturing its image was like trying to photograph a hummingbird in flight at night from thousands of miles away. Nonetheless, with ingenious algorithms and the combined power of radio dishes across the globe, the team produced a picture. Again, a glowing ring of emission, just a handful of pixels across, with a dark center about 52 microarc seconds wide on the sky. That angular size is equivalent to seeing a tennis ball on the moon from Earth. The image confirmed that our Milky Way's black hole is indeed about 4.3 million solar masses, and that the surrounding hot gas traces the distinctive signature of strong gravity, just as theory had foretold. It was a triumph of technology and of human patience, a profound affirmation that the unseeable can be seen. It was also a kind of coming-of-age moment in our study of black holes. These milestones, tracking stars orbiting an invisible mass, recording the ripples of spacetime from colliding black holes, and capturing the very shadow of a black hole's event horizon, are the culmination of a quest that began as barely audible whispers and scribbled equations. We have moved from speculation about dark stars and singularities to confidently mapping their influence in the real universe. Black holes are no longer hypothetical. They are concrete, observed entities that shape galaxies and shine, indirectly, across space and time. In the heart of our own galaxy, and in countless others, Supermassive black holes sit like silent engines, sometimes dormant, sometimes blazing if fuel is available, but always anchoring the cosmic structures around them. And yet, for all we have learned, black holes remain deeply enigmatic. We can measure their mass and spin and observe how they affect their surroundings. But what actually lies inside the event horizon remains a mystery. What happens to space and time at the singularity, where densities and curvatures approach infinity? How do black holes warp the flow of time itself? And what does that mean for anything or anyone that falls in? There are profound questions about information and entropy, whether information that falls into a black hole is truly lost or somehow preserved, that have led to spirited debates and new theories. These are paradoxes that have challenged the greatest minds in physics, puzzles still unsolved. Standing now on the threshold of a black hole's shadow, having seen its silhouette and heard its space-time rumble, we are reminded that we are only at the brink of understanding. The event horizon, that shrouding one-way boundary, beckons us to wonder what lies beyond its veil. Every new observation brings us one step closer to the truth, even as the fundamental mystery deepens. Our expedition through the realm of black holes has carried us from the death of giant stars to the hearts of galaxies, from tiny stellar remnants to light-devouring behemoths. We have felt their gravitational tug on starlight, heard their whispers and roars across the vastness of space, and even glimpsed their eerie silhouettes against the glow of the cosmos. With each discovery, the universe invites us onward, further into the unknown. Now, driven by relentless curiosity, we prepare to venture even closer to the edge of these cosmic abysses. We stand at the very brink of a black hole's grip, poised at the threshold of the event horizon, where the next chapter of understanding awaits, in silence and in wonder. We drift silently through the void of space, gradually approaching an immense darkness ahead. The black hole looms in front of us as a patch of starless night, a sphere of nothingness silhouetted against distant starlight. There is no solid surface that we can see, only the event horizon, the invisible boundary where even light is trapped by gravity. Unlike some voracious black holes that blaze with swirling disks of hot gas, this one is mostly quiet, announcing itself only by what it hides. Around its edges, starlight from behind the black hole is bent and warped, forming a subtle ring of light encircling the darkness. In the quiet of our spacecraft, we feel a deep, gentle pull, a tug of gravity guiding us toward the edge of the unknown. Even at a distance, the black hole's presence makes itself known in peculiar ways. Space around it is distorted. The familiar patterns of constellations ahead are subtly twisted and displaced. That faint halo of light we see near the black hole is an Einstein ring. Rays from stars hidden directly behind the black hole are being curved around by its gravity, converging toward our eyes. It appears as an ethereal band marking where space-time itself is being bent. As we continue forward in calm fascination, we remain alert to every change in our surroundings. Our journey carries us ever closer to that silent abyss, and with each passing kilometre, the feeling grows that we are crossing into a truly new realm. Inside our vessel, time flows steadily. Our hearts beat slowly as we remain weightless in freefall. The approach feels smooth and eerily calm. There is no turbulence, no sudden shift to mark the boundary ahead. Only the growing size of the black void in our viewport tells us how far we have travelled. In theory, we know that once we cross the threshold ahead, there will be no turning back, no way to return to the space we came from. Yet at this moment, it feels strangely peaceful. The silence of space and the steady forward motion give a sense of inevitability, as though we are being softly drawn into a deep, cosmic sleep. As we get closer, gravity's pull grows stronger, though we still feel no discomfort. Floating in freefall toward the black hole means we hardly notice our own weight at all. We remain almost completely weightless. We drift as if nothing has changed. But the readings on our instruments tell a different story. They register an intensely increasing gravitational field outside, the numbers climbing steadily with every passing moment. Our velocity, too, is increasing. We are falling faster and faster under the black hole's gravitational grip, though inside the ship we feel nothing of this acceleration. We are entering a realm of extreme physics where familiar rules begin to warp. Still, from within the craft, everything seems serene. The only hints of the black hole's might are the subtle distortions in starlight outside, and the quiet awe that settles over us as we venture deeper. The spaceship's windows reveal a sky that grows stranger with each passing mile. Stars that were once pinpoints now appear stretched into faint streaks and arcs of light. Directly ahead lies pure darkness. The event horizon itself reflects nothing, a perfect black circle cut out of the starry background. Yet around that void, the universe appears to wrap and curve in on itself. We see distant starlight bending, drawn into circles above and below the black center, as if space were a funhouse mirror warping the cosmos into new shapes. This surreal sight takes our breath away. It is beautiful and disorienting all at once, a cosmic optical illusion created by gravity's lensing power. Approaching the event horizon feels unlike any journey we have ever undertaken. There are no familiar landmarks or signposts here, just a steady intensification of gravity and the visual warping of everything we see. We know that just ahead lies the ultimate point of no return, an invisible threshold across which even light cannot escape. Our hearts quicken slightly at the thought, yet we remain enveloped in a strange calm under the black hole's spell. With each kilometer, we slide deeper into its gravitational embrace, the vast engine of darkness drawing us in. It is as if the universe itself is holding its breath as we coast toward this final frontier. As we draw nearer to this colossal void, we become keenly aware of its scale. Our instruments calculate that the event horizon ahead spans an almost inconceivable distance. This black hole has the mass of millions of suns, and its horizon could engulf entire planetary systems. Realizing this, we feel a mix of awe and smallness. We are tiny specks drifting toward a gargantuan warp in space-time. The sheer size and mass of the black hole defy our ordinary sense of scale, and a hushed reverence falls over us at the thought of such magnitude. We now pass through a remarkable region known as the photon sphere, the zone where even light itself can orbit the black hole. Here, the path of photons curls into closed loops under gravity's influence. For a moment, we witness an almost unbelievable sight, a faint glimmer that looks like a duplicate image of a star, light that has looped entirely around the black hole and come back to meet our eyes. It's as though the darkness ahead briefly offers up a ghostly reflection of the cosmos by bending light back on itself. This silent dance of photons is mesmerizing, a final strange beacon on the threshold of darkness. Beyond the photon sphere, only a small distance remains to the event horizon itself. That unseen surface lies just before us, not marked by any glowing edge or solid barrier, but defined by destiny. Cross it, and we cannot return. We pause in our thoughts, keenly aware that we are about to step through nature's one-way door. We take in one last grand view of the universe outside. Stars still sparkle in the distance, their light gentle and familiar, though subtly distorted at the edges of our view. It feels like a farewell to the world we've always known, a final glimpse of the familiar cosmos before we plunge into the unknown. Time itself begins to behave differently as we draw near this edge of the black hole's domain. We have been falling for what our onboard clock says is a certain span of time, but if someone were watching us from far away, their perception would be utterly different. To a distant observer, keeping careful watch on our descent, it would seem as though our approach is mysteriously slowing down. In fact, the closer we come to the event horizon, the more time itself appears to stretch out from the perspective of the rest of the universe. Our every movement, every heartbeat, would look slower and slower to someone at a safe distance. Inside our ship, we do not feel this distortion of time at all. Our clock ticks along steadily, and our bodies age at the only rate we've ever known, 1 second per second. Yet we understand that gravitational time dilation is at play. The immense gravity of the black hole warps not just space, but also time, causing the flow of time to depend on one's position in this gravitational field. This effect was predicted by Einstein's theory of relativity. A strong gravitational field makes time run slower relative to areas with weaker gravity. We actually experience a tiny bit of this on Earth. Clocks high in the mountains tick slightly faster than those at sea level, where gravity is a touch stronger. But here at the brink of a black hole, the difference is far beyond anything in everyday life. Our experience of time inside remains normal to us, yet we know by reason that relative to the outside world, we are moving in slow motion. It is a peculiar realization. Deep in the grip of gravity, we might exist in a stretched version of time, drawn out between moments. If we could communicate with a friend watching from a safe distance, we would soon notice strange effects in our conversation. Imagine we send out a steady series of radio beeps back to them as we approach the horizon, each pulse sent at regular intervals according to our onboard clock. At first, they would receive our signals in the expected rhythm. But as we sink closer to the event horizon, our friend would begin to find those pulses arriving farther and farther apart in time. The intervals between beeps would grow longer and longer, stretched by the gravity between us. What we perceive as a constant, steady stream of signals would, to them, become a slowing, almost languid trickle of information. Indeed, from that external viewpoint, we would appear to take longer and longer to fall as we approach the final boundary. Our distant observer might watch in perplexity as our ship's descent seems to decelerate more and more. Minutes would stretch into hours, hours into days, as our motion grinds nearly to a standstill. We draw ever closer to the very edge of the black hole, and then appear almost frozen in place. From their perspective, we asymptotically approach the event horizon, but never quite seem to cross it. It is as though time itself has paused with us on the brink. This is the strange nature of time near a black hole. What is a finite fall for us becomes effectively endless from afar. While the outside world would see us slow to a crawl, our own experience inside remains completely normal. Our journey continues smoothly, and our sense of time is unchanged. We feel no eerie slowing of our thoughts or motions. We might find ourselves wondering what is happening back in the rest of the universe at this moment. If we could somehow peer out at a clock far away, would it appear to speed up or do odd things? It's hard to discern directly, because any light reaching us from those distant clocks is also affected by gravity on its way in. What we do know is that we have entered a realm where time cannot be taken for granted as a universal constant. Each observer carries their own time, and ours has diverged profoundly from the time of the universe we left behind. In a very real sense, we are time travelers of a sort, moving into the future of the outside world faster than those outside. Even though we feel our moments pass normally, were we somehow able to leave the black hole now, we might find that far more time had elapsed in the external universe than had passed for us. Such is the power of gravity to twist the flow of time. To our friend watching us fall, we become an ever slower, fading image. And along with the stretching of time, another change becomes apparent. The colour of our ship's light shifts dramatically. If our spacecraft had bright white running lights, an observer far away would see those lights change hue as we descend. As we approach the horizon and our image slows, the glow coming from us grows redder and dimmer. Our once brilliant lights slide from white to yellow, to deep orange, then to a dull red. With each passing moment, more of the blue and green wavelengths are drained away, leaving only the long red tones. This phenomenon is known as gravitational redshift, the stretching of light to longer, redder wavelengths by a strong gravitational field. Just as our clocks have slowed down near the black hole, so too does any beam of light struggle to climb out of the intense gravity. One way to imagine it is to think of tossing a ball upward. As it rises, it loses speed, fighting against Earth's pull. Similarly, a photon, a particle of light, loses energy as it escapes the black hole's pull, and losing energy means its colour shifts toward the red end of the spectrum. Even light leaving the surface of our sun is slightly redshifted by the sun's gravity, an effect far too small for our eyes to notice. Here at the brink of a black hole, however, the effect is overwhelming. The light carrying our image outward surrenders more and more energy, its once short wavelengths being stretched into long, lazy red waves. As we draw closer to the event horizon, the reddening intensifies. Our ruddy image grows ever dimmer, shifting beyond red into the deep infrared range, wavelengths too long for human eyes to see. If someone were watching with infrared sensors, they would continue to see a faint glow from us a little longer, but soon that too would fade. The photons we emit become mere radio waves, gentle whispers that even the most sensitive radio telescopes would struggle to detect. Before long, all traces of us slip beyond the reach of observation. To the rest of the universe, we effectively vanish into darkness. No gleam of visible light, no faint heat glow, not even a radio signal escapes now with any strength. It is as though we are being erased quietly from the visible universe. Notably, this disappearance is not marked by any sudden flash or dramatic event from the outside perspective. There is no final burst of light, no explosive send-off as we fade. Instead, it's a silent, vanishing act. We simply grow fainter and redder until we melt away into the black. It's much like watching a sunset. The sun slowly dims and reddens, then slips below the horizon without fanfare. Here, we are the ones setting into the abyss. The process is gradual and inexorable. One moment we can still be seen as a faint red ember. The next, the darkness has swallowed even that last glimmer of us. From our perspective inside the ship, however, there is no such reddening of our immediate surroundings. The lights in our cabins still shine the same colour they always have to our eyes, and if we look at one another, we don't see anyone turned into a ghostly red silhouette. Gravitational redshift affects the light trying to escape from the vicinity of the black hole, but locally, everything behaves as normal. In fact, if we gaze out toward the universe we left behind, we might notice the opposite happening. The stars far above us, the light from the outside world streaming down into the gravity well, appear a bit bluer and more energetic than usual. This is gravitational blue shift in action, light gaining energy as it falls inward. A star that normally glows reddish might look distinctly whiter or bluer to us now, its photons compressed to higher frequencies by the time they reach our eyes. Even the gentle microwave glow of the universe's background radiation would be shifted to a higher energy, perhaps into a faint visible glow. So, while a distant observer sees our light drain to red and vanish, we inside might see the outside universe's light intensified and tinged bluer. It's a final twist of perspective, each side witnessing the other's light transformed by the black hole's gravity. We cross the threshold of the event horizon in utter silence. There is no jolt, no flash of light, no sharp boundary to announce our crossing. In fact, had we not been watching our instruments and counting down, we might not have realized the exact moment we passed through that invisible boundary. For such a momentous transition, it passes without any fanfare or announcement. But now that we are inside, one fundamental change becomes clear. Every link we had to the outside universe is severed. We attempt to send one last message, a brief signal back to the world we came from, but nothing returns, except static. Our radios fall silent. We are irretrievably alone. In that quiet moment, our thoughts drift back to Earth, to the people and places we left behind, under the warm sun and twinkling stars. We realize those stars are now forever out of reach, and a poignant mix of longing and acceptance washes over us. Yet despite the magnitude of this moment, everything around us remains calm and eerily normal. The black hole's pull is unyielding, but quiet, and we float onward as though nothing extraordinary were happening. This surreal tranquility in the face of such cosmic peril is almost paradoxical, a silent awe accompanying our fall. We find it both comforting and disconcerting that nature offers no dramatic sign as we slip deeper. Inside the event horizon, the very structure of space and time has shifted its character. Every direction we could possibly move now seems to lead further inward, closer and closer to the black hole's core. It's often said that once you're inside a black hole, moving forward in time means moving closer to the singularity at the center, and we cannot stop moving forward in time. In a way, space here is flowing like a rushing river, carrying us deeper in, and there is no shore where we can swim out to escape that current. Trying to fight our way back out would be as futile as trying to run up a waterfall that plunges endlessly downward. No matter how we orient our ship or fire our engines, we cannot reverse our course against the flow of space-time. The pull inward isn't just a simple force. It's woven into the fabric of the space around us. To even imagine escaping now, we would need to exceed the speed of light, which is utterly impossible. There is simply no turning back, no reprieve from the inward journey. The event horizon was truly a one-way door, and we have passed through it, bound for whatever lies at the black hole's heart. We turn our gaze back toward where we came from, or at least where we think outward used to be. Above us, there is still a glow, the last light of the outside universe peering in. It appears now as a shrinking patch of light against the blackness. That glow is essentially the mouth of the black hole, the opening through which we fell. As we plunge further inward, this opening to the outside sky contracts, as though the universe were slowly closing a curtain on us. The sight of distant galaxies and the familiar stars we once knew is confined to an ever-diminishing halo. It grows smaller and dimmer with each passing moment, and we feel a pang of sadness watching the cosmos we left behind recede from view. All around us now is a deep darkness, unlike any we have known. Aside from the faint glow of the receding outside world above and the soft lights of our vessel, nothing illuminates this interior space. The blackness is profound and perfect, a void stretching out in every direction, and yet it does not feel hostile. There is a strange serenity here in the heart of the darkness. We float onward, filled with a sense of awe. For the first time, we are beholding the inside of a black hole, and it is quiet and mystifying. The silence and stillness give us time to reflect on the wonder and peril of where we are. In this moment, fear gives way to curiosity and reverence. We are in the most extreme of places, and its quiet simplicity is strangely beautiful. Drifting ever inward, we begin to sense that the gentle conditions will not last forever. Gradually, the gravity around us is becoming uneven. The free-floating weightlessness we enjoyed starts to give way to a slight tugging sensation. Our feet, or the bottom of our ship, feel a stronger pull than our heads or the top. It's subtle at first, but unmistakable. The tidal forces are making themselves known. These tidal forces are similar in concept to the moon's pull that causes ocean tides on Earth, but here they are amplified to a horrifying extreme. Our vessel creaks softly as the differential gravity begins to strain its structure. Within minutes, those mild groans of metal grow into sharp, piercing complaints as the ship's frame warps under the stress. We exchange uneasy glances. We know this effect will only intensify as we continue our descent. The black hole's gravity is starting to show its true might, tugging and stretching us toward the center. Soon, we will experience directly what this growing force means for anything, or anyone, that falls this deep. Slowly, steadily, the stretching intensifies. If our ship were not strong enough, or if we were exposed outside it, we would feel our body being pulled longer and thinner with each passing second. The gravitational pull on our feet is now much stronger than the pull on our head, so our body would begin to elongate, joints straining as the difference increases. Our very shape would start to deform, stretching along the direction of the pull. Scientists have a grimly playful term for this extreme distortion: spaghettification. The image it conjures, of an object being drawn out into a long, thin strand like a piece of spaghetti, is exactly what is happening to us now. This unraveling of form doesn't happen all at once with a sudden snap. It increases gradually, though irresistibly. In a small black hole, the tidal forces would have become lethal long before now. A smaller black hole would start tearing apart an object even outside the event horizon. In such a case, an unlucky traveller would be ripped apart in space while still approaching the horizon, never making it this far. But our black hole is a supermassive giant, and it granted us a relatively gentle entry. We slipped past the horizon intact, feeling nothing at first. Only now, deep inside, does the gravity ramp up in earnest. The cosmic stretching truly begins to threaten our form. As the force continues to escalate, no material, and certainly no human body, can withstand it. Our spacecraft structure would eventually buckle and snap under the strain. Any person inside would be pulled apart, bone from muscle, molecule from molecule. Fortunately, this would happen so swiftly and overwhelmingly that unconsciousness would precede pain. A falling traveller would likely black out almost instantly as their body is wrenched into a long, thread-like shape. What was once a living, breathing human becomes a ribbon of matter, an elongated stream of flesh and bone turned into basic particles. All the familiar organization of the body is gone, overcome by gravity's relentless gradient. This extreme fate isn't reserved only for small objects like people or ships. Entire stars can be shredded in a similar way if they wander too close to a black hole. In fact, astronomers have observed such events in distant galaxies, a star being pulled into a glowing stream of gas as a black hole tears it apart. Whether it's a star or a person, the end result is the same: a long, thin strand of matter spiraling down into the black hole's depths. No intricate structure, no solid form remains, only a stretched out line of atoms rushing inward. What used to be our traveller and our ship is now nothing more than a faint trail of particles on the final leg of their journey. All of it is headed for one ultimate destination: the singularity, the mysterious heart of the black hole. At last, all paths converge at a single point deep inside the black hole: the singularity. This is the central point of the black hole's gravity well, and according to Einstein's theory, it's where the mass of the black hole is concentrated. By all calculations, such a place has almost unimaginable properties. It is a point of infinite density and infinitely small volume, where the pull of gravity becomes nearly infinitely strong. Our traveller, or what remains of them, is now inexorably headed into this ultimate abyss. Here, space and time as we know them are being stretched to their absolute limits. But what exactly is a singularity? In the pure mathematics of general relativity, it's a location where the curvature of spacetime becomes infinite and the known laws of physics break down completely. It's not a tangible object in the usual sense, but rather a sign that our equations are telling us something has gone terribly beyond the norm. A singularity is essentially where our model of reality reaches a point it can't handle, spitting out absurd results like infinite density. Our minds struggle to picture this: a place with no size that can somehow contain the mass of a star. It is a concept on the edge of imagination, a place where the truth of what exists is cloaked by our lack of understanding. It's as if space and time themselves collapse at that point, losing all meaning. For any object falling in, that singular boundary marks the absolute end of its story, the end of time as far as that object is concerned. Importantly, the singularity is forever hidden from the outside universe behind the veil of the event horizon. No light or information from that central point can reach an external observer. Thus, we have never observed a singularity directly. We only infer its existence through theory and by watching how the black hole affects its surroundings. This horizon acts as a cosmic curtain, ensuring that whatever happens at the core stays forever out of view. Interestingly, our universe itself may have begun from a kind of singularity in the form of the Big Bang. Conditions of extreme density and energy existed at the start of time, not unlike what we suspect inside a black hole. This parallel is intriguing. The very birth of our cosmos and the interior of a black hole might share similar mysteries. In both cases, the known laws of physics reach a breaking point, beyond which we currently have no clarity. Physicists suspect that the appearance of infinities in our equations is a sign that general relativity is incomplete. At such extreme scales, quantum effects likely come into play, meaning we probably need a unified theory of quantum gravity to truly understand what happens at the core of a black hole. It is as if the singularity is a signpost indicating where our current science must give way to new understanding. Many scientists believe that in reality, the mass collapsing inside a black hole might not form an infinitely small point. Quantum physics might intervene to prevent a true infinity. The core of the black hole might form an extremely dense, yet finite structure, rather than a mathematical point. There are even speculations that instead of collapsing to a true point, the core might transition into something unexpected, perhaps forming a bridge to another universe, a kind of wormhole, or even rebounding as a white hole that ejects matter back out. These ideas, however, remain purely theoretical, without any evidence to support them. Standing at this threshold of the unknown, we come face to face with the limits of human understanding. Our imaginary traveller's journey effectively ends here, dissolving into a mystery that even our best science cannot yet unravel. From the outside, all anyone ever observes of a black hole is its influence on the surroundings, perhaps a swirling disk of hot material around it, or the way its gravity bends the light of nearby stars. In 2019, an international team of astronomers captured the first ever image of a black hole's shadow, using a network of radio telescopes to glimpse the silhouette of the event horizon against a glowing backdrop of gas. Yet even this historic image could not show what lies at the center. It only reinforced that the heart of the black hole is a dark secret. Everything that falls inside remains beyond our direct gaze and seemingly beyond return. In 2015, scientists detected gravitational waves, subtle ripples in space and time, emanating from the collision of distant black holes. This discovery confirmed a major prediction of Einstein's theory and showed that black holes merge as expected, sending tremors across the cosmos. However, these ripples told us only about the outward properties of those black holes, their masses and spins, and nothing about what happened to the matter deep inside them. Even with such cutting-edge observations, the singularity itself remains unseen and unexplained. This profound ignorance gives rise to some of the biggest questions in modern physics. One such question is what really becomes of space and time at the singularity. Do they simply end, or do they transform into something beyond our understanding? But perhaps the most famous puzzle is the fate of information. Is everything that falls into a black hole gone forever? Or could information somehow be preserved? Stephen Hawking famously proposed that black holes aren't completely black. They can slowly emit energy in the form of Hawking radiation, meaning that over unimaginable spans of time they might eventually evaporate away. If that is true, it raises a paradox about whether the information of everything that fell in gets out with that faint radiation, or is lost inside forever. Right now, no one knows the answer. In principle, quantum physics tells us that information can never be truly destroyed, which is exactly why this apparent information loss is so puzzling. It's a conundrum at the intersection of quantum mechanics and gravity, highlighting how much remains to be understood. As we leave our traveller to their unknowable fate at the singularity, we are left with far more questions than answers. Instead of a tidy conclusion, we feel a sense of awe at the cosmos's ability to guard its deepest secrets. The singularity represents a frontier for science, a point where our understanding breaks down and something new and profound is needed to go further. Rather than seeing this as a defeat, scientists view it as an invitation, a challenge to expand our knowledge and find the new physics that will illuminate what a black hole's heart truly is. For now, the mystery inside the black hole remains, silently beckoning future explorers of the mind. Our journey into the black hole's grip ends here in uncertainty, but the quest to comprehend these cosmic enigmas continues. In the darkness of this unknown, we find not an end. Instead, It is the beginning of new wonders yet to explore. In the silent depths of space, a black hole seems like the ultimate one-way trap. Anything crossing its invisible edge was thought lost to the universe forever. But decades ago, a remarkable insight began to challenge this dark assumption. A young physicist named Stephen Hawking discovered that black holes might not be perfectly black after all. For generations, this was the prevailing view of a black hole. It would swallow matter and energy and never give anything back. Such an object was seen as a simple, inert endpoint of gravity's power, described only by its mass, spin, and perhaps electric charge. No trace of what had fallen in could ever emerge again. A black hole, according to classical physics, could only grow or remain the same, never shrink or dissipate. Physicists even summed it up with the phrase, "black holes have no hair," meaning no information other than those basic properties could be observed from outside. Working through intricate equations, Hawking found that a black hole can emit a faint glow of its own. From the surrounding vacuum of space, particle-antiparticle pairs are constantly appearing and vanishing. In the immense gravity at a black hole's edge, this quantum dance can be disrupted. One of these twin particles can fall into the hole while the other escapes, stealing away a tiny bit of the black hole's energy as it flees. Even what we call empty space isn't truly empty. The vacuum, according to quantum physics, seethes with transient particles popping in and out of existence. Pairs of particles flicker briefly into being and then cancel out. They are called virtual particles, and under normal circumstances, their ghostly presence goes unnoticed. But the immense gravity near a black hole's horizon can pry these pairs apart. One particle tumbles into the hole, while the other escapes, becoming real and carrying away a tiny bit of the black hole's energy as it departs. Hawking's breakthrough did not come out of nowhere. A few years earlier, a physicist named Jacob Bekenstein had boldly suggested that black holes possess entropy, essentially a hidden store of information, proportional to the area of their event horizon. This was a startling claim, implying that black holes, despite appearing so simple, had an internal complexity. Hawking himself was initially skeptical of this idea, as it challenged the notion of black holes as oblivion where no information survives. Around the same time, other hints were emerging. In the early 1970s, scientists like Yakov Zeldovich and Alexei Starobinsky proposed that rotating black holes could spontaneously create particles and emit energy by a sort of quantum vacuum friction. These suggestions were intriguing whispers in theoretical physics, but they lacked proof. It took Hawking's deep dive into the mathematics, blending quantum field theory with Einstein's gravity, to show definitively how a black hole could emit radiation. This escapee particle is part of what we now call Hawking radiation. It is a ghostly whisper of heat from a place that should have none. To an outside observer, the black hole appears to radiate energy slowly, as if it were a warm object in the cold of space. Paradoxically, the very emptiness around the hole contributes to its eventual undoing. The idea was revolutionary. Black holes are not eternal prisons after all. Instead, over inconceivably long times, they can leak energy and matter back into the universe. Hawking's revelation meant that a black hole has a definite temperature and entropy, which firmly links it to the familiar laws of thermodynamics. Bekenstein's earlier hunch about entropy was now vindicated. If a black hole has entropy, it must also have a temperature. And if it has a temperature, it must radiate some heat like any warm object. For the first time, gravity, quantum mechanics, and thermodynamics all converged in the description of a black hole. What was once thought to be a cosmic dead end began to look more like a slow transformation. When Hawking first proposed this idea, it was met with both astonishment and skepticism. Black holes emitting radiation was a concept no one expected, and for a while many scientists weren't sure what to make of it. There was no practical way to observe this faint glow, so belief had to rest on theory. Gradually, as Hawking's calculations held up and fit with broader principles, the community came to accept this profound change. The narrative of black holes shifted, from eternal guzzlers of matter to objects that could subtly give back to the cosmos and even eventually disappear. Black holes, it turned out, were not absolutely black after all. They possessed a nearly imperceptible glow, a whisper of radiation in the void. The very name black hole became a touch ironic, describing an object defined by darkness that nonetheless emits a bit of light. This surprising contradiction only highlighted how extraordinary Hawking's revelation was. Over time, as a black hole radiates, it loses mass. The once massive giant grows lighter and smaller, its gravity weakening. The loss is minuscule at first, almost imperceptible, but it is relentless. Eon by eon, the black hole that seemed so permanent begins to evaporate, dissolving like a slow mist under the morning sun. It is an almost imperceptible process, like a massive block of ice slowly sublimating into vapor under a distant sun. This process of black hole evaporation is far slower than any human timescale. For a black hole as heavy as a star, the full evaporation would take more years than our universe has existed by an astronomically huge factor. To put it in perspective, a black hole with the mass of our Sun would take on the order of 10 to the power of 67 years to evaporate completely, a 1 followed by 67 zeros. That is an almost inconceivable span, trillions upon trillions of times longer than the current age of the universe. Even heavier black holes would last longer still, essentially making them seem eternal from any human or even galactic point of view. In the far, far future of the universe, long after the last stars have burnt out, black holes will dominate the scene. Galaxies by then may have dispersed, and only black holes and the cold remnants of old stars will remain in a dark cosmic sea. During this epoch, those black holes will be slowly fading, losing mass at a snail's pace. They will be the final beacons of light, though a very dim light, in an ever-cooling, darkening universe. One by one, over stupendously long eras, even these mighty objects will wink out, leaving behind nothing but gentle radiation and vast emptiness. As the black hole shrinks, its fading glow intensifies. It sounds counterintuitive, but as the black hole loses mass, its temperature rises and it radiates energy at a quicker rate. In a curious twist, losing mass makes the black hole hotter and its radiation stronger. What was once a cold whisper becomes a warmer and more insistent signal as the end draws near. The smaller the black hole gets, the faster it evaporates, leading to a final burst of energy in its last moments. In those final moments, the black hole's remaining mass might be released in a dramatic outpouring of radiation. The ghostly ember that had persisted for eons could erupt suddenly like a dying star's last flare. After that brief flash, nothing of the black hole would remain, at least nothing we can easily see. It would have completely returned its mass energy to the universe as heat and light. For a fleeting moment, that diminutive black hole might blaze as brightly as a whole galaxy, though in the forsaken future cosmos there would be hardly anything left to witness it. Then, as suddenly as it appeared, that light would fade, leaving behind only silence and the memory of a once mighty star-eater. Yet, a profound mystery lingers around this ending. When the black hole vanishes, what happens to all the information about the things that fell into it? Every particle that crossed the event horizon carried unique details, information about its properties and state. Under ordinary physics, information is never truly destroyed. So, does a black hole's evaporation erase that information, or is it somehow preserved? This puzzle is known as the black hole information paradox. On one side of the paradox is the apparent loss of information, a troubling outcome, because it would mean a fundamental break in the laws of quantum mechanics. On the other side is the principle of quantum theory, that information must be conserved, that the universe keeps a kind of accounting of all processes. The fate of information in black hole evaporation pits these principles against each other. In physics, when we talk about information, we mean the specific details of particles and energy, the unique signature of everything that has happened. It's a principle of quantum theory that if you know all this information, you can in theory rewind time and deduce past events or predict future ones. Losing information would shatter that predictability. It would be as if the universe's memory had holes, with some events erased beyond recovery. That's why the notion of a black hole erasing information is so unsettling. It suggests a fundamental break in the logical bookkeeping of the cosmos. Stephen Hawking initially argued that information swallowed by a black hole might indeed be gone forever. To him, the Hawking radiation emerging from the black hole was purely random, carrying away no trace of what fell in. If true, the interior of a black hole would be like a vault of secrets that are lost upon evaporation. But many other physicists found this conclusion deeply unsettling. Over the years, a fierce debate unfolded. Could the universe really allow information to be deleted? Physicists like Leonard Susskind and Gerard T. Hooft argued that somehow the information must survive and be encoded in the Hawking radiation or stored in the black hole's horizon. The paradox became a central question in theoretical physics, inspiring new lines of thought about how gravity and quantum mechanics intersect. For decades, the question remained unanswered, spawning a rich tapestry of theoretical ideas and thought experiments aimed at cracking the mystery. Slowly, opinion shifted toward the idea that information is not destroyed after all. In 2004, Hawking himself conceded that a black hole should not obliterate information completely, suggesting that subtle correlations might allow information to escape in the Hawking radiation, though the exact mechanism remained obscure. This public reversal by the renowned physicist was a signal that the community was leaning toward information being preserved. In a humorous turn, Hawking even settled a long-standing bet on this issue by gifting an encyclopedia to a colleague, symbolically returning the lost information he once insisted would never escape. The information paradox opened the door to radical proposals. Until recently, physicists assumed that crossing the event horizon of a large black hole would be uneventful. Nothing unusual would be felt at the boundary. But the need to resolve the paradox forced a rethink of that assumption. To save quantum physics laws, some suggested a dramatic change at the horizon. Perhaps the event horizon is not the gentle veil we imagine, but something more violent. If such a firewall exists, it would radically alter what we believe happens at a black hole's edge. Instead of slipping seamlessly through the event horizon, an infalling astronaut would be met with a barrage of lethal radiation and be vaporized on the spot. All the information they carry would be violently scrambled and essentially reflected back out, rather than disappearing into the abyss. In this scenario, the event horizon itself acts like a ring of fire encircling the black hole, fiercely burning up matter and information to satisfy the demands of quantum theory. Einstein's theory of gravity includes the principle of equivalence, which says a person in freefall should feel no abrupt forces. Floating freely, they wouldn't notice crossing an event horizon of a sufficiently large black hole. By that reasoning, falling through the horizon ought to be uneventful and smooth. A firewall, however, would shatter this expectation completely. It implies that general relativity fails at the horizon, turning a tranquil passage into a collision with a searing barrier of energy that no traveller could survive. The firewall idea remains highly controversial and purely theoretical. Many physicists doubt that nature would create such an extreme feature, suspecting instead that a more subtle solution to the paradox will be found, one that doesn't require breaking Einstein's cherished principle. Nonetheless, the mere suggestion of a firewall has been useful. It starkly illustrated the depth of the dilemma and forced researchers to question long-held assumptions about black hole horizons. Whether or not a firewall truly exists, the proposal made one thing clear. Something fundamental in our understanding of physics will have to give or change in order to resolve the information paradox. Another hint at a solution came from a very different angle: the holographic principle. This concept suggests that all the information contained in a volume of space can be described on the boundary of that space. In the case of a black hole, it means everything that falls in might be encoded on the event horizon itself, like a cosmic ledger keeping track of entries and exits. It was a mind-bending shift in perspective, implying that the concept of volume might be an illusion at the most fundamental level. For a more tangible analogy, think of a hologram, a flat two-dimensional film that encodes a fully three-dimensional image. All the depth and detail of a scene can be stored on that flat surface in microscopic patterns. In a similar way, the holographic principle proposes that the entire three-dimensional contents of a black hole could be encoded on its two-dimensional boundary surface. To an outside observer, the event horizon would then hold a complete record of everything that has fallen in, like a cosmic ledger inscribed in the fabric of space. The holographic idea was inspired in part by black hole physics. Decades ago, Jacob Bekenstein noticed that the entropy of a black hole, a measure related to its information content, was proportional to the area of its event horizon, not its volume. It was as if the surface of the black hole held all the secrets of what had fallen inside. Initially, this seemed like a quirky detail, but it turned out to be a clue to a deep principle of nature. If the event horizon is a storehouse for information, then as a black hole evaporates, that information isn't lost at all. It could be imprinted on the outgoing radiation in incredibly subtle ways, preserving the cosmic ledger. In this way, no information would truly vanish, even as the black hole fades away. The holographic principle extends this notion to the entire universe, hinting that what we perceive as three-dimensional reality might fundamentally be described by information painted on a distant, two-dimensional boundary. Such a holographic view seems almost mystical, yet it arises from solid physics theories in quantum gravity. In one breakthrough, scientists found that certain kinds of universes have an exact holographic duality, a one-to-one correspondence between events inside a volume and information on its surface. This discovery gave credence to the idea that black holes, and perhaps all of spacetime, operate under holographic rules. This turned a far-fetched philosophy into a concrete principle, evidence that holography isn't just a wild idea, but a feature of consistent theories of the universe. For instance, physicists discovered that a certain theoretical universe with special properties can be described completely by a theory on its boundary, providing a real example of holography in action. Under the holographic principle, a black hole paradox becomes less perplexing. The lost information isn't really lost. It's just been stored in a different way. To an outside observer, all the data of anything swallowed by the black hole is encoded in the radiation and the fluctuations of the horizon. The interior of the black hole becomes like a projection, and the true record lies at the edges. This concept is profound because it blurs the line between what is inside and outside a black hole. It hints that our usual sense of volume and space might be an illusion, that the fundamental description of a region lies in its boundary. For black holes, it means they could be nature's ultimate hard drives, storing incredible amounts of information on their surface area. It's a profound reimagining of space itself, one that was born directly from pondering the mysteries of black holes. If this holographic vision is correct, it challenges our very sense of reality. It suggests that what we experience as three-dimensional space is akin to a projection, and that the true information defining our world resides on a distant cosmic boundary. In a way, we could all be shadows cast on the walls of the universe, with black holes serving as extreme examples of this hidden order. This idea sounds surreal, yet it has become a serious line of inquiry in modern physics, offering a tantalizing resolution to black hole mysteries. As ideas like holography gained traction, physicists saw black holes as more than just cosmic curiosities. These dark objects became proving grounds for our deepest theories. Any successful theory of nature, any unified description of quantum mechanics and gravity, would have to make sense of black holes and their mysterious behavior. In this way, black holes turned into gateways toward new physics. It is ironic that black holes, once doubted even by Einstein, are now central to the quest Einstein himself held dear, unifying the laws of physics. Albert Einstein did not live to accept black holes as real objects, yet his own theory predicted them. Today, these objects push scientists toward Einstein's dream of a single framework for nature. In seeking to understand black holes completely, physicists find themselves striving to merge gravity with quantum mechanics, continuing the work of unification that Einstein began. Solving the puzzles of black holes requires blending insights from the very large and the very small. In their extreme gravity and tiny size, evaporating black holes force us to use both Einstein's theory of spacetime and the quantum rules of subatomic particles. These theories, normally worlds apart, must cooperate when it comes to black holes. The effort to unite them is pushing science into unexplored territory. General relativity, Einstein's great theory of gravity, paints the universe on a grand canvas, smooth space-time curving around massive objects, following precise equations. Quantum mechanics, by contrast, deals with the microscopic, a world of particles and probabilities, where energy comes in tiny packets and uncertainty reigns. Normally these two realms are kept apart by their very different scales and rules. But in a black hole, the two collide, an immensely heavy object crushed to quantum scales. Here, the smooth fabric of space-time meets the jittery quantum foam, and our separate theories must somehow speak to each other. The quest for a unified theory, a quantum gravity that can describe black holes completely, has engaged physicists for decades. Some approaches, like string theory, suggest that black holes are not holes at all, but a tangle of fundamental strings or branes, which offers a microscopic explanation for their entropy and radiation. Other approaches, like loop quantum gravity, attempt to quantize space-time itself, potentially giving a picture of what happens at a black hole's core. For all their differences, each of these approaches seeks a deeper realm where the quantum world and the smooth fabric of spacetime unite into a single description. Each of these theories is tested, at least in thought, by whether it can resolve the information paradox and explain Hawking radiation consistently. Black holes have thus become a testing ground for ideas about the ultimate laws of nature. They bring together questions of quantum information, thermodynamics, and space-time geometry all in one package, demanding a single coherent story. So far, such trials take place only in the realm of thought and simulation, since we cannot directly experiment on black holes. But in the theatre of theoretical physics, black holes push each idea to its limits. One idea from string theory is that black holes are actually fuzzballs. There is no empty space or singularity inside, only a densely packed ball of vibrating strings. In this view, the material that collapses doesn't vanish into a point, but is spread throughout a complex tangle of fundamental constituents. The event horizon still marks the boundary beyond which we cannot see, but it's not a point of no physics. Rather, it's where this ball of strings ends. If true, the information about everything that fell in would be woven into the strings themselves, eliminating the paradox of loss. The hope is that a true quantum theory of gravity will tame the wild infinities of black holes. For instance, perhaps it will show that what we call a singularity, the infinitely dense center of a black hole, is not truly infinite at all. Instead, the singularity could turn out to be a realm where matter and space exist in some new, exotic state. This would resolve the long-standing puzzle of what really happens at a black hole's core. Such a theory could also shed light on the earliest moments of the universe, the Big Bang. In many ways, the Big Bang was like a black hole running in reverse, an unimaginably dense beginning that expanded into everything we see. In this sense, the final fate of a collapsing star and the birth of the cosmos become two connected mysteries, both pointing toward the need for a unified understanding of physics. Black holes, by demanding this new understanding, may guide us to insights about the universe's first moments and its deepest workings. What truly lies at the center of a black hole? Could it be a bridge to another reality? A fizz of quantum particles at the end of space-time? Or something beyond anything we've imagined? We simply don't know. It's questions like these that drive scientists forward, toward a single theory that one day might reveal the answers. Even as theorists wrestle with these enigmas, astronomers have been observing black holes in the cosmos, adding another perspective to the story. In recent years, they managed to capture the first direct image of a black hole's shadow, a dark circle outlined by a ring of glowing gas, confirming that these mysterious objects truly have the predicted event horizons. We have also heard the ripples of space-time as black holes collide, using gravitational wave detectors to sense the universe ringing like a cosmic bell. These observations have magnificently confirmed that black holes exist and behave just as Einstein's general relativity foretold, at least in terms of their large-scale effects. Yet, for all their spectacle, these observations remain silent about the black hole's quantum secrets. The orange ring of light in an image, or the distant vibrations of a merger, cannot tell us whether information escapes a black hole, or whether a firewall lurks at its edge. So far, we have no way to detect the gentle Hawking radiation that carries a black hole's secrets away over eons. Nor can we peek behind the event horizon. To answer those profound questions, we must rely on theory and imagination, pushing our equations to their breaking point and seeking new insights. One daring idea was to create tiny black holes in the laboratory using high-energy particle collisions. If such miniature black holes could be produced, they would evaporate almost instantly in a burst of Hawking radiation, offering a direct test of Hawking's theory. Experiments at powerful facilities like the Large Hadron Collider have looked for signs of these micro black holes forming, but so far, none have been detected. For now, it seems we must study black holes from afar, through our telescopes and our calculations, rather than creating them on Earth. Every insight gained from studying black holes reverberates back to our broader understanding of the cosmos. They have taught us that empty space can boil with activity, that gravity and quantum physics can merge to produce something startling. And they suggest that space and information are intertwined in ways we are only beginning to grasp. In trying to fathom black holes, we are driven to fathom the fundamentals of reality itself. Even as we struggle for answers, the presence of black holes in the universe continues to inspire wonder. They are reminders of how much we still don't know. Paradoxes made real, hanging in the sky. Each mystery they pose is a clue, guiding us toward a deeper unity in our physical laws. Slowly, step by step, black holes are helping physicists weave together a more complete picture of how the universe works. And much like their gravity, the allure of black holes pulls at our minds, refusing to let go until we uncover their truths. And so, the exploration goes on. The darkness of a black hole, once thought absolute, now shines with ideas and possibilities. From Hawking's revelation of radiance to debates over firewalls and holograms, black holes have pulled us into questioning the very nature of space, time, and information. These cosmic enigmas continue to hold our attention, promising that by embracing their mysteries, we may inch closer to the ultimate truth of our universe. Black holes still have more to reveal, and as we follow where they lead, we continue onward, ever deeper into the cosmic unknown. As our methods grow more sophisticated, perhaps one day we will find a way to truly unveil a black hole's secrets. We might detect the faint Hawking glow directly, or discover unmistakable evidence of how information is preserved at the event horizon. Until that day, black holes keep their silence, urging us to continue our quest and follow wherever their mysteries lead.